let's look at how we will go through today in 3 technical sessions, and the focus of the first session will be on how to better manage waste. That was also the topic, and based on your feedback in the poll, it is timely. We will initially start off with a summary of 5 research projects via presentations, then take a tea break, and then have a look at 2 more presentations. So Emma, I think everybody has the agenda with them, so they know the order in terms of the participants. Yes? Okay, good.
Yeah.
Now, to kick it off, we will have our colleague, Dr. Abbas. Dr. Abbas is with Butex, and he, of course, heads the department on the topic of chemicals. He's also leading the team with regards to executive development. He's a fellow with the Textile Institute. Many of you would have come across several of his research papers, but many of you would also be working with him because in addition to research, he's also very active as a practitioner. So Dr. Abbas, if you could take the many months of your work on RECARD, and if you could please compress it in about 15 minutes, which we understand is a challenging aspect, and take our participants through your project, will be very useful.
Thank you, Rakesh. Of course, I know everybody's in time pressure, and I will try to, be within 15 minutes. So thanks. And also thank you for introduction. Let me share the screen by myself. Yes, I think that would be good for me. Okay. Can you see this now?
Yes.
Yeah.
Yes, we can.
All right. Thank you very much. Good morning. Assalamu alaikum. Thank you all the participants who are coming over here, and also the organizers who has actually pushing the academicians and the practitioners to come together for last, let's say, 12 months. Thank you very much. So today I'm going to talk about a machine that we developed basically with the help of our students, which we termed as RECARD, and that machine will be using for carding action of recycled cotton waste. So let's go into one by one into that. Our research, these are the 5 persons, including me, who has worked in this project. Actually, they are the heart and soul of this project. 5 students they have started with me during their second year of undergraduate degree. So our specific objective was to develop a machine which can use recycled garment waste into a specific application. Now, what type of application, you will be amazed to see, and that has been come through a commercial, let's say, contractor. So they actually asked us to develop a machine for them, which could be used to increase the productivity of his business. And of course, because in Bangladesh, especially the textile machine manufacturing, the nascent stage for especially the textile industry, maybe with this could be a opportunity for the country, our students, and for the industry to be move into that value addition local machine manufacturing industry. Rakesh also shared in his opening presentation that waste is a challenge. There are 2 types of waste. One is production waste, and one is post-consumer garment waste. And we also showed in one of our paper that in the production, for every piece of garment export, Bangladesh has lost around 70 cents. And here we see the post-consumer waste, and Rakesh has shown is in his let's say just previous introduction that only 1% goes to the landfill. So different report shows different, but the fact remains is that only 8% and to 10% actually use, post-consumer garment waste has been actually used for recycling and reused. Let's say around more than 80% goes to landfill or incineration. And that is a huge, huge task. Especially for the Western countries where fast fashion has become a norm, let's say last couple of months, last couple of years. So let's say if we look into the now wasted garments, what is the option of wasted garments? One is we do the regular spinning with waste opener, and we do the carding and then rotor or ring spinning, and also we could do the non-woven fiber. So that is the usual process of post-consumer garment waste. In our case, you see the application will be used. This is a board. And you see inside the board, there is a gap in between the wooden panels. And they need to, because the water is a challenge when the boat is in the water. So they need to, fill it up with this cotton fiber. We could say this is a roving, and the more uniform it is better. And after, they put, let me use this laser pointer. After this, so this is the cotton fiber, cotton roving that we need to produce. Let me see. So this is a cotton fiber roving we need to produce. And after that they are going to put down into this spaces in between the two wooden panel. And after that, they will going to put down this, the coal tar things, so that it doesn't actually put corrosion into the water. So see, very specific application. And here you see these fibers that we have made from that machine. So when we started doing this this process of carding machines, we know that in market there are two very well-known company, Reactor and Tensile in Germany. They have two different models, C60 and C70, and TC11 and TC30. And we also have our jute carding. So we designed, when we consider what could be the carding machine for that particular application, we decided it should go with the jute carding. One of the reasons is because we do not want to put those cotton carding machines revolving flat bar, but we said probably we do not need the revolving flat bar. So for designing the machine, we have considered 5 different aspects, of course, many more, but impact on fiber through mounting work. This is a very interesting thing because the virgin fiber or raw fiber is stronger compared to the recycled garment waste. Recycled garment waste, by nature of use, post-consumer or production waste, usually have lower strength. So that means the wear should be, the action of the wear should be less the minimum compared to the raw virgin fiber. And that's why we decided that, go through the coarser things. Gauge distance between the rollers. So in a carding machine, which you'll see in, let's say in few minutes, that the roller distance between the, is very important for uniform action. Draft ratio between rollers, draft ratio, we actually finally considered around first to last. Feed to deliver is 47, but in between, feed to cylinder is 200 and cylinder to dopper is 2. So we have calculated different things. Angle between the roller position. Now there are 3 types of angles is found in a carding machine, especially the tooth position. One is positive, one is neutral, one is negative. And different scenario, different types of roller actually requires different types of angle. And we decided to have a neutral positions in some cases, and we decided to have positive or negative positions. Optimum dimension rollers. This is very, let's say this is a more practitioner things, because the dimension of the rollers, one is according to the design of the machine, but also what is available. Secondly, also if it is uniform throughout the length, throughout the diameter. So our development stages, basically 5 stages. First is planning and drawing. So you see that we draw the in hand first, and from there we decided how it should be look like. So you see the rollers, when you're saying there are different rollers based on this is a cylinder. There is a feed roller, taker in, striper, worker, stripper worker. I have 3 sets of stripper workers. And then finally dopper and dopper to delivery roller. This is the basic structure of a carding machine. And we decided what type of, let's say, distance supposed to be within, let's say, distance between the rollers. And also there will be a mounting wear on top of cylinder that that has to be also considered. So this is our planning stage, and planning stages we basically based on the standard jute carding procedure, standard jute carding machine procedure, but later we have to modify it according to what we get. Now, when the planning and drawing is done, our second step went to sourcing of the scrap materials. This machine has been totally developed based from the scrap materials that we have got in local, let's say local, I would not say local market, but local graveyard. So we go into the old Dhaka where this kind of things is happening. This kind of things has been found. You see the store. So we took around 2 to 3 months to get through this. Firstly, we didn't know where to get it. So finding the right information and right kind of parts, you see there are lots of different parts to be there, and there is a metal frame. The machine has to be set down in a frame. So we look for metal bars, we look for metal shafts, metal sheets. We look for this is a carding wire, this is a mounting wire that has been also from the second hand. You see we got it from a local factory, which they have discarded because they do not need to have them. We are looking for these different size of rollers from this different graveyards. All the parts that you would see in this machine, and all the rollers that you see in this design has been sourced from this scrap market. So nothing has been made here. And then our design is based on standard practice, but we are now doing based on other way around. So reverse engineering. So we are looking into what we have now, what type of cylinder we have, the size and dimension of the cylinder, size and dimension of the rollers, stripers, workers, all those. Now, based on that, we make a new design of these machines and with the new technical specification. And from the planning and drawing stage that we did in 2D, we actually try to visualize how it looks like, what it would look like, and based on that, we actually make a 3D drawing of this machine, but with the dimension that dimension is based on what scrap materials or scrap parts that we have found in the local graveyard. Here you see that ultimately the technical specification of the final machine came down to like this. Around 1250 to 710 millimeter, working with 500 millimeter. Production 20 kg hour is quite good for a sample machine, because the parts that we have is neither very small to sample or neither very big for the production machine. So I think this is a kind of optimum. Our input material will be garment waste, and input would be input speed would be 300 gram per meter. Output material will be thick strand of fiber, which can be turned into roving. Our total draft from delivery to feed to delivery will be 47, and overall power consumption would be 13 horsepower, something similar to that. So and now so when we source the materials, we designed the machine. Now it's coming to how to make this machine. Interestingly, the carding machine is the most challenging machine in spinning sector, because that has lots of different functionalities, different intricate parts, and different intricate, I would say, sophisticated, let's say, machining scenario required in terms of uniformity of the rollers, in terms of distance between the rollers, in terms of gauge. The local shop manufacturing are reluctant to do that, because of course 2 reasons. One is they haven't done this kind of sophisticated machine, but secondly also we do not have the money to spend on them, so that they can do it from the according to our design. So what we did is our students actually machined it in a local workshop for, let's say, 6 to 12 months in there. So they have been in between the classes, they went there, We purchased of course, this scrap parts. Also, we purchased, old motors, belts, pulleys, all those stuff. And then based on that, we requested in a workshop to put our machine in, and in there we use this different tools and machining to make the parts out of it. And it takes a long time, and the chain sprocket and all those stuff are supposed to be according to our specification, new design specification, and a student has done it. The next stage is assembly. Once the parts has been done, now put all those parts into a single machine. Now you see this is actually assembling of all those parts into a single machine. Assembling part of all those into single machine, and it is kind of so all the parts and assembling has been also done by our team, research team. You see all these parts has been grooved by us. Sometimes we took help from the local the workshops. Let's say we have taken their tools sometimes, and we put all the assembly machine, all the parts into a single platform. And there we also see the the fiber is actually feeding in there. This is the assembly took around around 3 to 6 months itself, because the frame has to be made accordingly, and from the frame all the parts has to be put down into a right positions with uniform distance and in uniform positions. And now the production begins, and trial and error has been going on. It's a very difficult task for us. There are lots of, you see, this is the feed. This is the garment waste, cotton garment waste based on there. And this is the delivery. This is the delivery. You see the delivery is here. Delivery is here. And so the idea is you put this. So this is also the cotton garment waste that is sourced from locally. So it goes into the feeding part of the machines, and then from there with lots of different actions, striper, dropper actions, striper workers and actions, and the dropper, we get the delivery out of it. But trial and error, we face numerous difficulties. I mean, the difficulties you can see that flying dust is actually all around there. We'll talk about this as well. But this is final machine, and this is final output. The challenges that we basically faced here is in the trial and error. We also have uneven feed distribution. The feeding of this fiber is not in terms of when we have the virgin raw materials. It's usually automatic, and also it's usually with certain depth. Certain depth means it is always a uniform feeding. Here it's not uniform feeding. That is one of the challenges that we faced during this production, that if it is manual feeding, and manual feeding means all the machine will be running in single cycle, but the feeding will not be according to the uniform. And when the feed doesn't be uniform, there are two issues. My delivery output will not be uniform, but also in some parts of the machine there will be material. In some parts of the machine there might not be material, or thickness of the material is low. That means there will not be any carding action. Now, if we look into some challenges that we face, the sourcing is a big challenge for us. Firstly, because a machine has to be developed due to the budget constraint from the scrap materials, and where to find that kind of scrap material. Cylinders, mounting wares. For mounting wares, you have to look for let's say factory to factory, because the wire is usually not actually, we are not getting it into the local market. But even if we get it, that wires are worn out and will not be serve our purpose. Dimension, as we said, the first design has been modified based on what kind of scrap materials parts we have found, and change the design accordingly. And the motors also coming from the old shop. So sometimes we are not sure actually we are getting the required power. Technical challenge is huge. First is machining. I mean, our research team has done the machining part and the finishing of the scrap materials, and we do not have enough experience for that, and we did not get enough support from the local workshop. So required size and shape with the proper dimension throughout the width or throughout the length is getting very difficult. Proper equipment also is important because we need the tools to assemble together. We need the tools to measure the things together, and we have to borrow all the time, or we have to guesswork. Rollers RPM, so I'm finishing quickly. Rakesh, I see your faces. So roller RPM also because one part is dependent on others. So finding out the right RPM to get the carding action is also difficult. There were numerous technical problems that we found. One of the just gave you one problem. Instead of delivery rollers, delivery rollers supposed to deliver our output towards, let's say, outwards. But instead of is delivering outwards, it actually taking it yourself and backing to the cylinder. And this problem has been there for 3-4 months, and we are not able to solve that problem initially. And then after discussing in various ways, trial and error, and then we are able to change some of the settings, and then again come back, the delivery has been done. There are some performance drawback as well. As I said, uneven feed materials, dust accumulation. So because this machine is not guarded, that means dust has been moving around in all the parts and moving around the room. Low precision, of course, low precision because as I said, the distance between the different rollers is supposed to be very uniform. But in our cases, it sometimes, say, for example, if it is supposed to be 0.25 millimeter in one roller to another, sometimes in one area it is 0.175, sometimes it is 0.3. That means the action of that particular point has been compromised. Complex maintenance. Now, when we designed the machines, we are more focused on our output to be there. But in many cases, maintenance because you see the dust accumulation, we need to let's say clean that. And also we need to, for wear and tear, we need to also open the parts. And we actually, initially, we haven't considered it. This is our first machine. Efficiency was not optimum. One of the reasons are because feed material is not uniform. So that's why, and also the second is also the precision is low, so efficiency was not optimum. So, so that's the machine development, and we can see the impact is, we are more focusing on the local machines. Local machine industry would be there, but also there will be a chance to use, local scrap materials parts for much value-added work rather than, let's say weight of the materials. So we purchase around more than 500 kg of those parts as a scrap materials, but a carding machine itself is a very, valuable commodity. Technology transfer. And also textile mechanical, but also this is a chance to use the recycled garment waste from the industry to produce, different application. And from there, discarding, it could be also possible to produce yarn, and that yarn can be because there will be subsequent other machines that has to be used. And from this, this web, there should be sliver, roving, and yarn. That could be also possible. So that's it. Thank you very much. If you have any questions, I'm here. Otherwise, thank you for listening.
Thank you, Dr. Abbas. I'm curious about one small point. How many rounds of trial and error did you and your team go through? Approximately, do you remember
hundreds.
How many rounds?
Hundreds.
Okay, thank you.
Hundreds.
Yes, okay, that was important to know. And there is one question from Mr. Mohammed Rakib Uddin. He's asking that your approach and this idea is interesting, and if you have any business plan, and if you had a chance to speak with the waste processors about this initiative of yours.
I mean, a very good question. This machine has been developed as a commercial contract. So that particular person actually asked us to do it. Now, the main question is, what's the plan for the next mission? I mean, what is the plan for next development, or is there anybody? I mean, we are very open to, open to the waste processor who have actually come to us, because the first machine has been developed and we feel that there are lots of area that we can actually improve. But as I said, based on budget constraint, I mean, if some commercial companies can come, and we could definitely work on that. Thank you.
Thank you, Dr. Abbas. All right, now having looked at RECARD, let's go into what our peers and our colleagues in Pakistan have been working on. We have Dr. Yasin Nawab from National Textile University. He leads the Faculty of Engineering there, yeah? And he's an expert on technical textiles. So he'll share with us, Dr. Nawab, thank you for joining. Thank you for preparation. It's interesting for us to know what you have been working on in terms of green composites. And we understand that you've spent many months of work on this. If you can compress it at about 15 minutes, that would be appreciated. Over to you, Dr. Nawab.
Thank you, Rakesh. Hello, everyone. In fact, it will be a very quick and brief introduction of what we are doing on textiles, especially with respect to sustainability, and then a brief introduction of our activities on textile reinforced composites, especially using textile waste. The National Textile University is a federally chartered public sector university. We are situated in Faisalabad near India. We are offering BS, MS, PhD programs, about 4,000 students, and we are the only specialized textile university in Pakistan. So our research focus is mainly on exploring alternative fibers which are more sustainable and local recycling in terms of garments, in terms of waste, in terms of like PET bottles and the things like this, development of green products, water reduction, energy efficiency, microplastics, etc. And we have one of the biggest resources, more than 50 PhD researchers who are in textiles who are working in different research centers. So if we come to textiles, our composite center is National Center for Composite Materials. We are working in this center since 2014. It's a team of 11 or 12 faculty members with some PhD and research associates. So in fact, we are exploring the complete value chain of fiber reinforced composites from plants, means exploring of fibers, development of yarn, fabrics, then matrices, and then composites and their testing. So we have a fiber lab for natural fibers as well as for synthetic fiber extrusion. We have multi-component weld spinning. Then in reinforcement, we have spinning, weaving, braiding, knitting, etc. For composite fabrication, almost all the techniques which exist, they are there. And then for lab facilities, we have a complete range of mechanical testing, thermal testing, and etching equipment. I will be sharing with you our work on the work of my students on textile waste and their conversion to composites. So if we talk about textile waste, currently it's about 110 million tons annually, which will be like increased to 300 million tons per annum by 2050. And only 15% of it is recycled, the remaining it goes to landfill. If we talk about waste, we all know there are two categories, post-industrial and post-consumer. If we talk about post-industrial waste, so most of it is recycled, but post-consumer today, its percentage, in fact, is very few, only 15% is recycled. Of course, there's a lot of focus, and hopefully in the next years, this percentage will increase. So composite materials, mainly they are combination of fibers and some polymer matrix. If we talk composites that we use globally, otherwise there are many things. So in the first work, it was published in Journal of Textile Institute. So what we investigated, it was making the composites using different types of waste like knitting waste, oil waste. Then we compared them with the glass fibers, and then we evaluated them. So globally, I would like to share with you very quickly that how much percentage of waste if we use, we can get the performance, required performance without a lot of compromise. So if you look at C9, these are the composites that we use a lot using glass fibers and unsaturated polyester. And these are the, in fact, composites that we made with the waste composites, and their performance is comparable. We talk about tensile strength. For natural fiber, impact energy and impact strength, in fact, it's normal because they are less brittle as compared to glass fibers. We talk about tensile, specific tensile strength. It's a little lower as compared to glass fiber, but it's in fact, you can say 20% lesser. And with 100% basis, it's acceptable. There is another project that we completed recently by converting post-industrial denim waste. It was an industrial project. So we converted post-industrial denim waste to floor and interior tiles. The composites were made with polyethylene and polycarbonate resins. We use thermoforming machine, and these are the in fact tiles or plates that we developed. So we developed samples with different fiber volume fractions: 64%, 57%, 52%, both types of resin. So we used small, like pieces of denim waste, a little bigger denim waste pieces, and then so these are the composites that we developed with with polyethylene. You can see these are like clear. You can see the rags within the plates. And these were the samples that we developed with polycarbonate. And even here, in fact, it's aesthetic. The design is, it looks very good. And for interior application and for floor tiles, it seems like beautiful. Then we like did their testing. This is, in fact, the tensile testing. So as expected with polycarbonate, as its strength is higher, so we get the composites with higher strength, tensile strength, and low strain. It means for floor tiles, these composites can be used. And polyethylene composites, they have higher strain, so means they can be used for interior wall covering. So then we check flexural properties as if we are using them as floor tiles. It was very important. So same, the strain in polycarbonate composites is lesser. It means they are suitable. Whereas PE, as I said earlier, they will be used as interior. Then we check their impact properties. So polycarbonate, their energy absorption with the denim bags, it was higher as compared to polyethylene. So finally, we concluded, and we are in the phase of upscaling it at the industrial level. The development of denim polycarbonate flooring tiles and denim PE tiles for interior. Then we did some study. It was use of textile waste of cotton and jute with glass to develop composite in order to check that how much percentage that we can use. So by 33%, as time is short, I will not go into detail and a lot of explanations. So with 33%, you can say 15% of jute and 15% of cotton. The properties, they were as required. There was not a lot of compromise. So here is another study that we did in order to check mechanical and thermal properties of glass composites, and we used waste cotton and flex based with them. this article, it was published in Journal of Industrial Textile. So what we did, we use a specific sequence, stacking sequence like glass, glass, glass at the face, then flex, paste, glass, glass, glass. So in fact, the stacking sequence, it was very important. We wanted to put a glass at the top in order to avoid like degradation and water absorption by the natural fibers. So if we look at the results by using 10% of cotton waste and 10% of flax waste with 80% of glass, the results, in fact, they were very good in terms of tensile strength and modulus, in terms of flexural properties, 10 cotton, 10 flax, 80% of glass. So the value, in fact, it was very good. Same was we did also their thermal characterization. It's very important, especially in the environments like India and Pakistan, where it's very hot. So composite, they expand and their shape distort with temperature. So with 80, 10, 10, the thermal expansion, it was a little. It means composite, they will maintain their shape and their structure with increase in temperature. There is another, I think it's the last study I will share with you briefly. We use the waste fibers in the concrete and we check their mechanical performance. So we developed concrete without fibers. We used waste for polyester fibers, polypropylene fibers, and glass fibers. We were not using cotton and natural fibers because natural fibers, they degrade with moisture. Their life, in fact, is not very long. So polyester fibers and polypropylene fibers, they were collected from the textile industry waste, and glass fibers, they were collected from the composite industry. So we did the required testing for composites, for concrete. So this is the compressive strength, which is one of the important factor. So with glass fibers, the compressive strength is high. We used 2% fibers, 4% fibers, and 6% fiber. So PP and PET, they were followed by it. If you can see it, so we use PP, polypropylene, its percentage is not very high. But if we use it, so the increase in compressive strength is evident. This is without fibers. All these values are with fibers. After 4%, in fact, if we use more, there is problem of wetting and dispersion, due to which the strength decreases. Then we have flexural strength. Glass is the highest, followed by polyester and PP, etc. This was the reference sample. So whether you are adding PP, whether you are adding polyester or glass, our values, they are higher as compared to the reference sample, means the sample that contains no fibers. Then we did an impact testing as well, and for all the fibers that we added, the impact strength increases. So it was highest with glass, followed by PET, and then polypropylene. So it means we have a lot of use of polyester in textile industry, so we can recycle it in form of fiber. We use in fiber reinforced composites, or in construction industry, it gives very significant and very promising results. So this is in fact a summary. We can use the textile waste in value-added in a value-added form in composite. The portion of textile waste can be incorporated in composites is about like 10 to 15% if we use. So we don't compromise a lot of results, but we get some increment in the properties. And if we are using like waste, one very important thing to consider is treatment of fibers and their like dispersion or good mixing of waste in the matrix you can say the concrete or in the polymer is very important. So best option is to use waste in hybrid composite, means you use waste, you use some other fibers, and 10 to 15% it can be. Of course, by using waste of 10 to 15%, the performance it improves. Thank you very much.
Thank you, Dr. Nawab, for firstly being perfectly on time, but also for sharing with us how this waste, which was not being processed, was given a new life and became part of the life of another product. Thank you very much to you and your team who worked on this and for sharing your work. If you could please stay on for a few minutes, and if there are any questions coming in the Q&A box, we will direct it towards you. Thank you, Dr. Nawab. Yeah? All right. Some textile waste is added to another product and these composites. Let's talk once again with regards to how textile spinning waste can be addressed. Yeah, this is also what we see in terms of the response to the poll question. So once you have a chance, please share your feedback there. Your feedback was to address post-industrial or pre-consumer waste first. So for that, we have Dr. Abubakar Siddiqui, who's with Booft University, who's going to share with us how this topic is being addressed. He is the professor and head of Department of Textile Engineering, also at the European University in Bangladesh. And at the same time, he's also the national expert in the Department of Textile under the Ministry of Education. He also is supporting the University of Stuttgart and ITV Denkendorf as a scientific officer. And he's involved with a wide range of research activities along the entire textile production chain. So Dr. Abubakar Siddiqui, if you can please share the outcome of your work again in about 15 minutes, it would be very useful for us. Thank you.
Okay, thank you so much. Can you hear me?
Yes, yes, we can.
Okay, thank you. Okay. First of all, thank you so much, everybody. And good morning. My topic is recycling of spinning waste and garments recycling, plastics recycling, and renewable fibers. Can I share myself, or you can share?
Whatever you prefer.
Okay, you can. Next.
Okay.
Okay, this presentation is part of my habilitation, my postdoctoral thesis in the framework of the HEST, Higher Education Network for Sustainable Textile. I mean, last project. My special thanks to BMJ, GIZ, DRD, and Technical University Chemnitz, because they have given me a chance to do this work. My theme is sustainability in textile and RMG processing in Bangladesh. Next, please. Project objectives: recycling of textile spinning waste, garments recycling, and new biodegradable fiber development from waste, recycling of thermoplastic materials, renewable and alternative fibers, and fiber composite development. Next, please. Textile spinning, actually, in our country, two types of material we are using. Polyethylene terephthalate, polyester, and cotton. Next, please. Please, perhaps we can skip this also. Go next. Okay. It can vary, but more or less waste from spinning from blowroom to blowroom carding, drop frame, left former, comber, simplex waste, ring frame waste, winding waste. Simplex ring frame and winding waste, these are hard waste, especially we use another way. Please go next. Okay. Recycling of cotton spinning valuable waste, especially common oil, carding, blue duffing waste. We are using in rotor spinning and other use also, some fancy yarn also. Please next. Now we can use our research, some disposable waste as composite material. Here we have manufacture already composite. This is substitute of synthetic material. Please next. And composition of this biodegradable matrix is water, straws, cooking oil, and reinforced fiber. Next, please. And we also produce compost fertilizer from spinning dust or waste. Next, please. And recycling of cotton disposable hard waste, especially from dust particle, we can separate cotton, and from also from ginning waste, we can use 100% cellulose, because in cotton, the 100% cellulose we can get. So this is the source of regenerated fiber like viscose, bottle, kipo, lyocell, acetate fiber manufacturing. Next, please. Okay. In our lab, we have manufactured viscose fiber, model fiber, CMC, acetate fiber, kipo fiber. Next, please. This is the schematic diagram of viscose manufacturing. We have already wire spinning machine here. So we have manufactured viscose fiber here in lab scale, but we want to go to commercial scale. This is from garments waste. Garments waste, first garments dyed fabric or clothing, stripping, then different ways, bleaching, scouring, bleaching, then other process, then, like viscose or anything, any regenerated fiber. Okay, next, please. Here's the. Please, you can skip this because this is the old one, I think. Okay. This is the manufacturing schema of chitosan coated viscose fiber. We have added chitosan for antibacterial or better comfort clothing manufacturing. So this is the modified viscose manufacturing process. Next schema, please. Next. This is the method of CMC manufacturing. Step 1, step 2, step 3. Almost same process, but here is the acetic acid, acetic anhydride. No, this is a carboxylic group we have introduced. Okay. The next, please. Perhaps this is an old one. I have given last night one. Can I share from me? Please. Recycling. Is it okay? Can you see? Okay. This is the manufacturing schema of acetate fiber manufacturing. And this is the regenerated fiber, 5 regenerated fiber. We have the FTIR diagram, comparative diagram of FTIR, recycle garments, recycling of thermoplastic material, because this is the hot topic of our country. We have 2 big industry here in our country from thermoplastic material recycling, like polyethylene, polypropylene, polyester. I have one company, DART Group, cooperation with Honorable Chairman of DART Group. So I have manufactured some fiber in our laboratory. We have a mill spinning machine, and some of fiber from DART Group. There is the machine of DART Group, and some sample from DART Group. And here's below is a non-oven machine from our laboratory. We have also this, we can manufacture here from cotton, non-oven, polyester, polypropylene. So mostly we produce here in laboratory. Some sample taken from DART Group. Here I have so many results, but I cannot show you this time. I'll show it in my postdoctoral thesis. So I have renewable fiber, almost 24 fibers I have worked with this, and some physical properties here also mentioned from bamboo fiber, coir, lofa, palmyra, kapuk, maize, others, then enough, banana, sisal, rami, hemp, abaca, silk, kapuk. So the renewable fiber, first we started here in 1916, first innovated the banana fiber manufacturing machine here in Bangladesh. And we have produced fiber and yarn in our laboratory, mainly up to fabric yet not, because fabric is fine fabric we can not manufacture here. But we are trying to, but we have successfully manufactured this non-oven from our laboratory for the baby diapers and sanitary napkins from garments waste. And the banana fiber. Obviously, initial cost is high, but this is the most valuable product. This product developed from BFT by our own researcher. Very simple method. After stiffing, then scouring, bleaching, then nanopaint. It's a very easy process, and we are trying to develop this new product. And I have sent some of fiber to my colleague, Dr. Stegmaier, ITB Dengendorf. He has tested tensile strength and soil test. After 10 days, I had the microscopic view. After 10 days, some degradation occurred in lemming fiber, and other fiber, and they show that cocos fiber is best result from ITB Dengendorf. So we are trying to use a renewable this waste fiber or disposable fiber. Conclusion and findings: it has been utilized waste of RMC and disposable plant as a fibrous material and brought value added product. In our research are going further into manufacturing of multifunctional valuable product and sustainable oils. That's all from my side. Thank you so much. Thank you for question. And reference book is used from myself is natural fiber from me, and this is the sustainable textile and fashion value. Chapter 18, there's also by me. So that's all. Thank you so much for your attention and patience. Thank you.
Okay. Thank you, Dr. Siddiqui, also for sharing your knowledge in a concise manner, comprehensive manner via these books and publications. We appreciate it. Now, having looked at the waste from spinning waste and so on, let's look at how the wastewater from the dye bath is being addressed. And for that, we will have Dr. Sher Jamal Khan, who's with the National University of Science and Technology based in Pakistan. Do we have Dr. Khan with us? Yes, we do, yeah. So
yes, I'm here.
Some of you would know him from his previous work because he's also been working with the industry for a while, along with his current assignment in the Nust University in Pakistan. He also holds a doctorate on environmental engineering and management from AIT in Thailand. And he's been working on projects that address water treatment, biological aspects, water quality monitoring, and so on. And he has also had a chance to work on projects together with global international organizations like UNICEF, WWF Pakistan, Nestle, and so on. So, Dr. Khan, if you could share the outcome of your work in about 12 to 15 minutes with regards to how the textile dye bath is being looked at and how it can go towards zero liquid discharge, it would be great.
Thank you very much, Rakesh. It's a pleasure today to be part of this international symposium. It's an honor for me and at the Nust research group working on textile wastewater treatment, working almost now for almost a decade, working on the textile wastewater, its recycling and reuse potential. So the presentation topic that I will be covering today is the reconcentration and reuse of textile dye bath effluent using surfactant-driven forward osmosis to achieve zero liquid discharge and hazardous chemicals discharge. So this is the topic I'll be covering today. Just a small introduction about Nust. It is the premier engineering university in Pakistan. It ranks #1 in engineering. And the group that I'm heading here, we are primarily focused on domestic and industrial wastewater treatment, recycling, and reuse. The added feature into our research group is now resource recovery. And that's what we will cover today in this presentation. So I have to change the slide, or okay, so great. So next slide. So this research team that I would like to emphasize, which is particularly working on this topic, that is being led by me, is supported by my MS student, Maria Yasin. Excellent. She's a gold medalist, undergraduate engineering, and now working in my research group as the lead student. She's being supported by Dr. Saqib Nawaz, as Dr. Saqib is a postdoctoral researcher, at the King Abdullah University of Science and Technology, Saudi Arabia. Actually, I would like to emphasize that he was the one, my first PhD student, who started working on textile wastewaters. And now we have an association of almost a decade. Dr. Saqib Nawaz is again being supervised by Dr. Nuruddin. He's a full professor at KAUST, and again, researcher, a lead researcher on different aspects of wastewater recycling and reuse, especially in the areas of forward osmosis and membrane distillation. So with this introduction to the research team, next slide, please. A small introduction to what type of waste we are looking at. So it is 230 to 270 tons of wastewater that is being produced for 1 ton of fabric that is fabricated. So, believe me or not, that is almost contributing 20% of the global wastewater production in the textile sector. And this is a lot of waste. Since we know that textile industry is a heavily water consuming industry, consequently, the waste production is also resonantly very high. The major areas where this wastewater is being generated is from the dyeing and finishing processes. And more importantly, textile effluent is having a high pH value, high in chemical oxygen demand, and intense color. More than these effluent concentrations, we have an issue that there's a portion of the inorganic components in the effluent of the textile industry, which is extremely difficult to handle and treat. So we cannot just consider a textile wastewater as any conventional wastewater, especially the dye color contributes immensely to this waste and makes its treatment consequently not very easy to handle. So such a discharge of wastewater, untreated wastewater, can have a huge impact on the flora and fauna. It has a huge impact on the public health, and that's why its treatment becomes so much necessary. Next slide, please. So what is the need? We need to have a protection of the environment. And how can we do that? It is by looking at what we need to treat and how to treat. So now just coming to the textile effluent pollution, current dyeing processes has a very low fixation. And this low fixation results in a high amount of dyes that are being discharged into the receiving water bodies. Especially the type of dyes that have been reflected on the slide. Most importantly, the wet dyes and dispersed dyes, they are only 70% soluble, and 10 to 20% are actually, then are lost during the dyeing process. The good part is that even during that dyeing fixation process, there is, no chemical change. So it means that if we handle this waste, in a professional and manner, the change of the chemical composition of the dyes remains the same. So it is something possible that we can recover these dyes from the waste that is being generated. Next slide, please. So just to add to this, we are looking at something that needs to be addressed because this is a huge amount of waste that is being generated, So now we are not only looking at, treating the waste for recycling purposes, but also to reconcentrate the dyes. So currently, the biological processes that are being used, these processes are mostly biological in nature. But unfortunately, in a biological process, the dyes are actually destructive towards the microbes, and that results in a high hydraulic detention time for the biological process. This increases the space requirements, this increases the operational cost, and then the dyes, may produce something that is carcinogenic in nature. So now, how do we handle the biological process if we have to reconcentrate, the dyes from the spent bath? One way is through the nanofiltration membranes, which has been investigated in the past. But these membranes, they are high in energy consumption and high in fouling. They also produce hydraulic pressure, which may lose the integrity of the dye. So considering some of these disadvantages, today we are looking at membrane filtration processes in the context of forward osmosis, which are low pressure processes. Natural gradient is being used, and this has the potential to reconcentrate the waste. Also, the forward osmosis has low fouling potential, which makes it more attractive towards the reconcentration of the dyes from the spent bath. Next slide, please. So the research objectives that we investigated included the optimization of the flux in the SDS draw solution. SDS is one of the draw solutions that we investigated. The reason for its selection is because it's used in textile industry. Next is the investigation of the reverse route flux, the dye concentration, and the transfer across FO membrane. Analysis of the SDS concentration in the diluted raw solution, the characterization of fouling and scaling on the membrane surface, and lastly, the Nmr analysis. That's what I will cover briefly in today's presentation. Next slide, please. So we investigated two types of dye bath wastewaters, the denim dye wastewater and the polyester. Both of them are extensively, types of wastewaters that are, generated from the polyester and the denim industry. So we would like to look at both of them, and that's what we prepared synthetically. We simulated it in our lab so that we could investigate at the lab scale and get the results, and then we can comment and have a discussion on that. So that's what we prepared and investigated in our study. Next slide, please. So now coming to what we investigated, this is our experimental plan. So what we did, we first varied the feed solution temperature 40, 50, 60. That allow us to optimize the temperature of the feed. Then we went to optimize the temperature of the draw solution. Then we investigated in varying the feed solution concentrations, the draw solution concentrations, and of course the feed solution was varied between wet dyes and the dispersed dyes. Both types of dyes extensively used in the denim and polyester industry. Next slide, please. So this is the schematic illustration of the setup. Here, what you can see is the feed solution that is being depleted, and the draw solution, which is the draw solution, where you can see the draw solution volume increase over time. We used the weighing balances, which were connected to the electronically, so that we could record the change in, which could record the change in the draw solution. And also we used a hot plate so that the temperature can be varied also. You can see that all this process was automated. We had a conductivity probes, we had a data logging manometer, data logging setups. Everything was integrated into the system so that we have a continuous working operation of this lab scale, system. Next slide, please. So this gives you an overview of the actual setup in the lab. So all the components that were showed, previously, here you can see them in physical form as well. Next slide, please. We had the samples analyzed on a very, kind of a regular basis, and the type of analysis, that was being performed included the pH, the color, the COD. We did the scanning electron microscopy, and also lastly we did the NMR analysis to see how the dyes behave over this course of this investigation. Next slide, please. So this is the setup of the scan electron microscopy. Now coming to the very interestingly the results. Next slide. So here you can see that we varied the temperature of the feed solution, and what we found was that by increasing the feed solution temperature, the flux of the membrane process, that is the FO membrane flux increased. And resultantly, main reason is because the viscosity of the feed decreases, so that resulted in the increase in flux of the feed. Looking at the draw solution that was used, varying the draw solution temperatures had no significant impact on the flux. So one could very easily understand that since textile wastewater generates roughly between 45 and 55 degrees centigrade, so any temperature within this range helps in achieving high flux for the FO membrane. So next slide, please. So now going to the next thing, results is the flux variation with the feed solution and draw solution. Here again, what we found was that if we increase the feed solution concentration, that will constantly decrease the flux on the, and again, the impact that is for the dispersed dyes. For the wet dyes, the variation in the feed solution concentration did not have a huge impact. But when we looked at the draw solution, when we increased the concentration, you can see that up to 0.75 molar concentration of the draw solution, that is SDS, there was a significant impact on the increase in flux, but beyond 0.75 molar, there was no change. So you can consider that 0.75 molar concentration can be considered as optimal for the feed concentration of SDS. Next slide, please. So this is an overview of what we achieved in terms of the dye concentration and mass transfer. I consider this is extremely important slide because of our system design and our experimental plan. We were able to recover 80% of the wet dye and 67% of the dispersed dyes that were concentrated using the SDS as the draw solution in the FO process. And this is almost this, similar results have been reported by other researchers as well. So we could consider that this is, a very, commendable kind of a, result where we could not only treat the wastewater, but we were able to recover the dyes as well. And also, we could remove the 96% of the COD from the system. So, of course, the COD removal depended upon the pore size of the membrane, but again, good removal of the COD and the excellent dry recovery were the two important outcomes of this research. Next slide, please. Just one important thing. So we also could say that the reverse route flux in all experiments was low. And this is also something very much important because this allows the process to work over time in a sustainable manner. Next slide, please. This is also an important slide where we could see that at 0.75 molar concentration of the SDS concentration initial, final concentration still had an SDS concentration between 32 and 35 grams per liter. And this diluted raw solution can now be reused in different textile processes. Since SDS is a surfactant emulsifier that is primarily used in a wetting agent and detergent in the textile industry. So this diluted SDS can be further diluted in the industry and can be used for the purposes as just mentioned. Similar type of work has been reported earlier also, where the desizing, scouring, and bleaching processes uses a concentration of 2 grams per liter of the SDS. So you can very easily understand that now this diluted SDS is another resource that can be reused in the industry. So now, at one hand, using the FO process, we could remove the COD, we could recover the dyes, and also the diluted SDS can be used in the textile industry as well. So we are not generating any waste whatsoever, targeting the zero liquid discharge. Next slide, please. So this is scanning electron microscopy analysis, and just to mention that, of course, the membrane fouled over time. It is something inevitable, but this fouling was controlled because of the conditions that were reported earlier. But this just shows the fouling trends of the FO membrane in our investigation. Next slide, please. The NMR analysis, this shows that the original dispersed dye and the recovered dye had no chemical change in its composition. So this is extremely good result, because now we are not only recovering the dyes, the chemical composition of the dyes also, it didn't change over the course of the process. So it means the dyes we are recovering, they are not only being recovered, they are still maintaining its integrity in terms of its chemical composition. Next slide, please. So coming to the conclusion of today's presentation, I would like to emphasize that we were able to recover 80% of the wet dye, 67% of the dispersed, and this was being reconcentrated using the SDS as a draw solution in the FO process, which can be reused in the next batch of the industry. Next result was that the maximum flux was achieved as using SDS, and we achieved the highest flux of 6.3 liters per meter square per hour as a draw solution, with a reverse solute flux of only 0.035 grams per meter square per hour. Next major conclusion was that there was no functional change in the dyes that were recovered that was proven by the NMR analysis. Lastly, 30 to 35 grams per liter of SDS was present in the product water, which can be reused in the desizing, scouring, and bleaching processes of the textile industry. So this is all which what I would like to present today as conclusions. And for future applications, we would like that this lab skill study is upscaled to actual industry, so that we could further elaborate the results that we achieved in the lab, and further emphasize how it further can support the achieving of the zero liquid discharge for the textile industry. So thank you all very much for listening, and if there are any questions, I'll be more than happy to listen to you. Thank you very much.
Thank you very much, Dr. Khan, for sharing, first of all, about your university, about the setup that you have, and also about this experiment. I'm sure there will be many eager brands and factories who would want to try it out, what you've achieved. Thanks for that. Now, having looked at the aspect of reconcentration and reuse of textile dye bath, let's go on to the next topic with regards to optimization of the electrocoagulation process in order to remove color and turbidity. And for that, we will have Dr. Sarit Ban. Dr. Sarit Ban is with the institute in Cambodia, and he currently heads there, the laboratory. He's also the researcher there. He takes care of the Faculty of Hydrology and Water Resources Engineering at this Institute of Technology of Cambodia. Dr. Ban, over to you. If you can please share in about 12 to 15 minutes your work, it will be valuable.
Okay, can you hear me?
Yes, yes, we can.
Okay, thank you so much for your introduction, and hello, professor, and all lecturer or researcher who are present in this conference. My name is Redbon. I'm from Water and Environmental Engineering of Institute of Technology of Cambodia. And today I'm very happy to be here in order to present one of my research topics related to the textile wastewater. And my topic, the presentation today is optimization of electrocoagulation process for color and turbidity removal from textile wastewater by using the design of experiment methodology. So my presentation today quite not very long, since I have we the schedule is a little bit late. So here is the outline of my presentation today that I mainly divided into 4 parts. Okay, let's move to the first one is introduction. As we know that industry is one of the key development sector for the economic of the country. And at the same time, since the population and the economic growth, that it is very sense that we need a lot of industry production. So during the population and the economic growth, the urbanization and the industrialization is also increasing. At the same time, there is a lot of water consumption and wastewater disposal into the environment. So a lot of water consumption, the same that the wastewater production is a lot. So usually when we're talking about the wastewater, color wastewater is also one of the main concerns due to the different type of the industry, such as the textile or dye operation industry, from the food processing, from the even the slaughterhouse also produce the color wastewater. And if we take a look in Cambodia, Cambodia also one of the country who are in the top 10 exporter of the clothes. So mean that Cambodia also one of the country who have a lot of textile wastewater. Mean that the garment industry factory a lot in Cambodia. So if we take a look into the environmental aspect, we found there is a lot of color or dye wastewater has been produced. And usually, if we consider about the problem of this one, I think most of us are clear that the dye contaminants are quite toxic to the ecosystem, also the aquatic life, and also affect to the environment that require a proper wastewater treatment. And in the common treatment, there are various treatment technology that have been applied for the textile wastewater treatment, such as the coagulation, flocculation, the advanced oxidation process, the iron exchange, also about the membrane filtration that have been just presented. And also electrocoagulation is also one of the treatment methods for removing the color as well as the textile wastewater treatment. Electrocoagulation process is one of the common process. Due to this process, there is no additional chemical required. Also related to the capital investment cost related to the flux performance. The flux is a little bit higher, also the stable flux, and also the operation, it is more easy for operation and maintenance. And if we taking into the limitation or the challenge of the electrocoagulation process, we found that even though it has been applied for industrial scale, but the fundamental mechanism of the process is still the main challenge in order to optimize the operation condition. As we know that electrocoagulation process is one of the high energy consumption process and require optimization in order to minimize the energy. So the objective of this study is to optimize the reactor configuration and the operation condition of the electrocoagulation for treating the color and turbidity from the industrial textile wastewater. So this one is mainly about the treatment method using the electrocoagulation, but I mainly focus just about the optimize using the design of experiment methodology. So here is the overview, but I think since the time limit, I'm not going to present all. I think for the part 4 and part 5, I may skip, and I will go through just part number 1 about the optimization and the kinetic. Okay, here is my experimental setup that I use in my lab, and I call it the electrocoagulation reactor. It diverse design as from the acrylic at the lab scale to contain around 14 liters of the wastewater. And there is an internal loop similar to airlift reactor. There is an internal loop, and I put the electrode inside the reactor, inside the small internal reactor. And we expect that there will be a reticulate between the small and the big column. And in the design of experiment, we are used the response surface design in order to optimize the experiment. Since this one is one of the techniques that commonly used for modeling, also the analyze, in order to optimize the response of the investigated factor. And I use the software Minitab 17 software for this purpose. And this table shows the four factors that were investigated, and also the factor level that ranking from the low, middle, and high. That commonly we call it -1, 0, and +1. So these are the 4 conditions that we can vary for the optimized purpose. Okay, I have skip some slides, so I will go directly to the result. Okay, let's go to the first one is the optimization for the turbidity using the electrode, aluminum electrode. Since there are 2 electrodes that will be used in this study. One is aluminum and one is the iron. So the first step I optimize by using the aluminum electrode in terms of turbidity. So based on the statistical analysis, we found that the voltage and the operation time factor have significant effect on the turbidity removal efficiency. And we found that at the higher voltage and higher operation time, the treatment performance is better. But for the insignificant factor, we also observe their optimum condition also. We found that at the lower level of the gas and the gas flow rate, we found that at the lower is better. It's better, as you can see in the main effective plot in the right hand side of this slide. Okay. And the second one, I also observe to optimize the main effective factor, mean that the main factor that we found from the previous slide. So this one I will optimize by using the optimization tool in the software also. And we found that the high voltage and high turbidity up to 30 volts and 70 milli, the maximum removal efficiency was obtained, and it is around 99.24%. And after we get this condition, we will go to other level is using the iron electrode. And the same thing in the factorial analysis, we found that the three factors, the two is the same from the aluminum electrode, voltage and operation time. But at this time, we found that using the iron electrode, the electrode gap also affect significant effect to the turbidity removal. And we found at in the close, we can say the low gap, the performance is much better. And the removal efficiency, we can optimize up to 98.36% of turbidity removal. Okay, let's see to the next step is for the color. For the color, we also analyze in terms of the voltage, in terms of operation time, in terms of gap, and also gap flow rate. However, we found that one factor, operation time, or we call electrolysis time, is significant effect to the treatment performance. And the voltage is, the p-value is higher than 0.05. So just higher a little bit. So we are not going to count as the significant. So we found only one is the main factor, is the operation time or electrolysis time. However, we also observe, the treatment performance as the optimization study. And I see select voltage also, since we want to get at least two parameters to study in optimization. So at this one, after we apply at the optimum, at the optimum condition, 30 volt and 55 minutes, the removal efficiency of the color can be obtained around 20%, around 20%. And if we use the iron electrode, we found that all four factors are affected. All four factors that we investigated are affected to the removal efficiency or removal performance. So we can optimize this four. And this four factor, we found that, okay, around 30 volt of the supply voltage, at 2 centimeter of the gap, around 0.5 of the gap flow rate, and around 70 minutes of the treatment or electrolysis time are the optimum conditions for the color removal using iron electrode. Okay, here is the surface plot of each factor. Surface plot for each factor in terms of color removal using the iron electrode. And using this one, the removal efficiency can be obtained around 16.7%. Okay. So in this slide, I just summary for all of investigative factor, and also the optimum condition that I found. Okay, after we got the optimum condition, I will study the kinetic study for each condition. In this slide, I study the kinetic study of the turbidity removal at different initial concentration, and we fix the supply voltage. And from this result, we found that at higher initial concentration, a slower removal efficiency was observed. And it may relate to the coagulant dosage supplied to the system. In order to remove around 20-50, in order to remove to less than 20 MTU turbidity, up to 550 MTU, we need around, this one is 70, not 700, 70 minute electrolysis time. And if we supply at different voltage, and we found that voltage is significant effect to the treatment. And if we investigate at different using the same, we found that the result is not much different. I think because the turbidity is quite easy to form the flux, so around 30 volt is sufficient. Even though we try to increase more, it may be not very significant. And for the color, we also investigate at different initial concentration, and faster color removal performance were observed at the lower initial concentration. And in order to use the highest color concentration, we need around 380 minutes quite long. And here's the summary for the kinetic study from this investigative work. So I summary what we have studied and the optimum condition we found from the kinetic in order to reduce the color initial concentration, to color concentration, also the turbidity level to lower the standard. And okay, and the last part of the result is about the empirical correlation. Mean that after we optimize, we can fit or we can simulate our experimental condition, experimental result to be the empirical model for the future estimation. So we have produced two for turbidity, one using the aluminum electrode and the other one use the iron electrode. And this one we also simulate for the color removal using the aluminum and the iron. Okay, let's go to the last slide about the conclusion. So I conclude that the optimum condition of the electrocoagulation, we found around 30 volt of voltage, 20 centimeter of the electrode gap, 0.5 lit per minute of the gas flow, and around 70 minute operation time. And under the optimal condition, we found that the turbidity around 99%, and the color around 20% can be removed. And at different electrolyte time are required for different initial concentration. Moreover, I have some suggestions. One is, since this work we use the synthetic wastewater, synthetic dye wastewater, so it would be suggested for the future study to test to dry. Now, actually, right now we are testing with the actual wastewater. And it's second one, since this electrocoagulation is just a single one, just the single one for the single system without the separation. So in the future, it should be studied together as the integration system between electrocoagulation and sediment or separation process. The third one is the kinetic model should be constructed, because I study only the optimized model, not the kinetic model. And the last one, the sensitive analysis of my empirical model should be analyzed also in order to understand about the level of the error of the model. Okay, thank you so much, and I'm sorry that I summary a lot because I have the overlap schedule. Thank you.
No problem. Thank you very much, Dr. Saratban. I'm sure that many who are facing the challenge of color and turbidity in the wastewater will find the outcome of your study useful and would like to try it out for corrective actions. Thank you for that. Now it's time for a short break before we go on to the next interesting topic of microplastics. How it can be used via the RECARD program, and then having looked further into what happens with textile spinning waste, how it can be used with green composites, but also how to extract color out of the dye bath after the wastewater, and how to take care of this wastewater to go towards zero liquid discharge. Now let's talk about the topic of microplastics. As many of you would have seen that this is also a topic of high interest with the policymakers in Europe. And so for us now, we will hear from Ms. Humaira Akhtar Himu and Mr. Tanveer Mahadi from Butex about how their work is looking at addressing the aquatic microplastic pollution issue. So it's over to you.
Hello, everyone. Good morning. Can you hear me clearly?
Yes, we can.
May I request Dr. Rakesh, is it okay if I share my screen so that I can present my presentation?
Of course, sure, Tanvi. And if possible, Tanvi, take us through the many months of your work in about 12 to 15 minutes, yeah?
Yeah, sure. I'll try
you.
my best. Thank you. So can you see my screen?
Yes, we can.
Yeah, okay. So hello, everyone. At first, I'd like to offer my sincere gratitude on behalf of my team for giving us the opportunity to present our ongoing work. Myself, Tanvir Mehdi Deep, along with my fellow researcher, Ms. Humayra Akhtar Himu, will present our work today. The theme of our work is aquatic microplastic pollution that we are getting from the domestic washing of the textile substrates. That is when the end users are washing the textile products. Sorry. The whole presentation will cover the following topics. We will start off by introducing the microfibers and microplastic pollutions, and we'll show the importance of our study in the first part of the slides. And in the next part, we will describe our work and how we are conducting the experiment with our materials and machines and other characterization techniques. So we all know that microfibers are really the small fragmentations of fibers. It can be defined as the fibers having length less than 5 millimeter, or in terms of denier or count, we can say that microfibers have count less than 1 denier. So the microfiber holistically covers both the natural and the plastic parts or the synthetic parts, but microplastic only covers the synthetic elements which are less than 5 millimeter of length. We can get microfibers in two ways. The primary microplastics are concerned with the chemical degradation or abrasion or release of the fibers from the synthetic textiles like products. So our study is concerned with this primary microplastic, while the secondary microplastic is concerned with more like natural phenomena, while the bigger plastic particles are getting degraded by weathering or wave action or wind or UV radiation. Those we will address as the secondary microplastics. From this figure on the right hand side, we can get a better view of the size and the implication that microplastics can have on our ecosystem. So we can see that the plastics in the micro or nano scale level, they are actually smaller than stuffs like fish eggs or larvae and sands and sediments. So they are very small. So we can say that they are very difficult to track, and also the nanoplastics which are less than 1 micrometer, they can easily break the cell barrier and get into our blood and brains, and thus causing damage to our body. In the next slide, I have tried to show why we are addressing this. Seawater is probably the mostly victimized by the microplastic pollution. A study has found that almost 5.25 trillion microplastic pieces with a combined weight of 268 metric tons were found in the seawater. So an average person is reported to ingest almost 6,000 plastic debris annually. This has been found in a study, and the left side image show that how that microplastic is available in all around us, and how we are absorbing the microplastic in our body by various factors. And also, this statement is reinforced by the state that almost 81% of the tap waters that are used in the household activities are contaminated with microplastics. And most of the hard drinks manufacturers and sea salt samples proved that microplastic is found in all of them. So we can understand the severity of the microplastic from these findings. Also, the textile laundry is concerned in this matter because of all the marine microplastics found, almost 35% were reported to come from the textile laundry only. So this is an estimated total of 2 to 13 million tons per year microplastic that are found in the marine environment comes from the textile laundry wash waters. And microplastic is dangerous for us because they are mostly synthetic toxic components, and they can be a medium for transporting the toxic metals, heavy metals, pathogens, and other things. And thus they can attack the sensitive parts of the body, like, for example, our immune system, our reproductive organs, or other neurological organs and other organs of our body. So in the right side image, we have tried to show how microplastic is getting released from the textile synthetic cloths when we wash it with or without detergent in the washing machine. They get out in the water. Our effluent plants cannot remove the microplastic to 100%. They maybe can remove 50% or in that area, and thus the rest of the microplastics are getting mixed with the different water sources and thus ending up in our food chain. The next slide reports. We all know that we have found from the studies that at least 50 billion pieces of apparels are made worldwide annually. And we use almost 70 million tons of fibers to make them. Out of approximately 63% are from synthetic sources. So this is a very important data. So we can estimate the amount of microfiber released every year from the textile garments only. And on the left side, I have tried to show a statistics that was conducted in 2018 by region, how many microplastics we are using in textile and how much of them are getting lost in the environment. By getting lost, I tried to show you that these microplastics cannot be captured by different techniques like effluent systems, and they are getting mixed with our environment and thus ending up in our body eventually. So we can see that more than 50% in every region, in almost every region, we can see that the microfibers are getting lost and we cannot recover them. And also from the last year's report, we can see that although there was a long break and shutdowns and lockdowns due to the COVID outbreak, we saw that the demand of the cotton and polyester staple fibers still increased by 2% almost, while the other fibers demand decreased due to the COVID outbreak. So we can understand from this figure that how much demand is increasing for the fibers, even though we have encountered a lockdown like COVID-19. Now, why microfibers are dangerous? So we can see that microfibers covers both natural and synthetic part, but the natural part gets degraded very fast compared to the synthetic parts. So they are here to stay. So if we do not capture or recover microplastics in the various processes, they will get released and they will sustain for a long time and thus contaminating our ecosystem. So the evidence is in front of us. The recent news have covered that microplastics are being found in human body, in our various sensitive organs like in blood, in our lungs, and in our tissues. So it is evident that microfiber is really running rampant throughout the environment. So what we are doing? Actually, we are doing many things to stop the release of microfiber, or at least reducing them. However, they are not enough. I'd like to point your attention towards this figure, where the efficiency of different techniques used by different scientists to stop the release of microfiber showed that only in the region of 50, 30, and 20%, they were able to efficiently reduce the microfiber in the textile laundry wastewater. And on the left side, I have tried to show two types of washing machines that are available in the market. They are top-loaded washing machines and front-loaded washing machines. And the top-loaded washing machines are reported to shed more microfiber than the front-loaded washing machines, at least 1.5 times more. Now, coming to our research topic, we are solely focused on the aquatic microplastic pollution due to the release of microfiber during the consumer stage washing. So when the end user or customer is buying a cloth and washing it in its household, how much microfiber is being released, we have tried to show that. So our research objective includes some of the topics like primarily we have tried to estimate the microfiber release by weight. So how much microfiber is being released by weight from a washing cycle, to find out the microfiber loss in relation to washing cycle. So we have conducted a few washing cycle of the same sample to understand how the release is decreasing in every cycle. We have also tried to compare the microfiber release for different types of clothing. For example, we have tried to take a different composition and different construction of the fabric, and thus wanted to understand the release behavior of them. Also, we have differed the washing conditions, like we have washed with detergent and high temperature, low temperature, and thus we have tried to understand the implications of different washing conditions. And finally, we'll try to calculate the environmental load from the aquatic microfiber release. So how much load is being exerted on the environment due to this release. In this work, what we have done, we have tried to replicate the home laundering. So how we are washing the fabrics at our homes, we have tried to replicate that to understand better the real scenario of the microfiber release in the environment. We have taken different factors like fabric type, different types of fabric we will use and we are using. Washing conditions, different washing conditions, like I mentioned in the last slide, with or without detergent or varying the temperature, we will take the microfiber release behavior. And washing cycles. At different washing cycles, we will capture the microfibers. And another thing we did, we used a membrane filter with a pore size of 0.22 micrometer, which is the smallest pore size we could find in the market. And we have used this to make sure that we captured the maximum of the microfibers released in the washing stage of the fabric or garments. To briefly outline our methodology, we started with sample preparation and we prepared a sample to be elaborate. We took a particular weight of the sample and particular size of the sample, and we will use this weight and this size to understand, to directly compare them. And sample washing technique was resembled as per our home laundering system, and we have used this sample with detergent, as with detergent the sample tends to shed more microfiber. Then we have, after washing the sample, we have collected the wash effluent, the after wash wastewater, and we have also rinsed the sample before collecting the effluent. So we have subjected the sample 2 times. Once we have washed, and then we have rinsed them with a number of water. We have conducted 2 phases of filtration system. The first phase with a bigger filter pore size, because we wanted to capture the bigger fibers that are being released due to the wash before going to the microfiber stage. So we use the Whatman filter paper with pore size only 11 micrometer. And on the second stage, we have subjected the same effluent wash water through a membrane filter with 0.22 micrometer filter. And we measured the weight of the filter papers before and after filtration to understand the weight of the microfiber released during that washing cycle. So we have repeated this process in quite a few 2 or 3 times to understand the trend of the microfiber release in every cycle. And finally, we have analyzed the filter paper with things like scanning electron microscope, FTIR, and polarized microscope to understand what types of microfiber is there on the filter paper and the proportion of the natural versus synthetic microfiber release behavior. Now to the next part, my colleague Ms. Humaira Akhtar Himu will continue. Thank you.
Thank you, Mr. Rakesh. Thank you, Deep. Can you please go to the next slide?
Yes, and Ms. Humaira, thank you for those background about how you set up the program and the process. If you could please make a short summary and conclude in the next 3 to 4 minutes, yeah, so that we have at least a minute for Q&A.
Okay, thank you.
Thank you.
So my colleague Deep has already informed that our work is basically ongoing. So we are today we will focus the results and discussion we have got so far. Here initially we have taken a fleece knit fabric, and we take a specific sample size. I will tell the reason why we take, and please go to the next slide. We used a portable mini washing machine because here you can say that the size of the capacity of the machine is only 1.8 kg. Here is the main challenge we faced in our planning stage, because during domestic washing a huge volume of water is discharged. So if we cannot collect the whole volume of water, then we cannot quantify the amount of microfiber released during domestic washing. That's why we choose to use this low capacity washing machine, and that's why instead of taking the whole garments, we cut the piece of garments and take a 24 into 24 centimeter size, and then cut the edges, and the cut edges are folded and stitched to avoid open edge fiber release. Then please go to next. Yeah. And after collecting the whole discharge, we have taken 2 phase filtration. The first phase we use Whatman filter paper, that is 11 micrometer pore size, here to collect the large size fibers which we can see the naked eyes and other suspended particles. Then this filtrated water we filter using the membrane filter. Here is the pore size 0.22 micrometer. Then please go to the next. Now please next. We have visualized the filter paper which we found, and the left side shows the Whatman filter paper visual observation after filtrating 500 ml water and then filtrating 1000 ml water, and then I like to mention that we will continue our work same wash cycle up to 10 washing same sample, but as it is ongoing up to now, we have already done up to 3 wash cycle and found this result. Please go to next. As I mentioned earlier that we have taken the amount of released microfiber using an analytical balance. At first, we taken the weight of the blank filter paper, and then after filtration, second phase filtration, we oven dried the filter paper, and then again taken the weight. And here you can say that there is a gradual degradation of the amount of microfiber we captured based on the cycle, based on the washing cycle. And the for sample 1, we found 8.3 milligram of microfiber released from first cycle. And then for the sample 1, in case of second cycle, we found 7.5 milligram, and then for cycle 2, we found 4.2 milligram. And we replicate, we do the same process for sample 2. Sample 2 is basically the same fabric from the same garments, another fabric from the same garments to check the reproducibility of our result. And we found that the gradual degradation of fiber release based on wash cycle. Please go to next. And we have visualized the final filter paper surface with an optical microscope to see how to count the number of microfiber released. And we found from cycle 1 that we cannot take the whole dia. We took a random sampling from the whole filter paper, and we found that total 42 cotton fiber found in 8 millimeter dia of cut pitch of filter and 1 polyester. And from the same filter paper, we found 64 cotton and 1 polyester, and another for 1 we found 64 cotton and no polyester. Please go to next. And we found the same thing for cycle 2 also. The amount of cotton fiber is high. Shading of cotton fiber is high than polyester. Next, please go to next. And also for cycle 3, we found the same scenario. Please next. From this diagram, we can see that the number of cotton fiber shredding is higher than the number of polyester shredding during domestic washing. Please go to next. In this figure, I like to show the trend of microfiber release in relation to wash cycle. As we only done 3 wash cycle. So in case of sample 1, for cycle 1, the amount of fiber found is high, and chronologically after cycle 2 is gradually reduce the amount, and then cycle 3 is again reduce the amount. And we will do this after 10 washing cycles. So we can say that number of microfiber release decreases with the increase of wash cycle. So, as our work is not completed yet, so we will do further analysis, similar type of studies for different composition of fabric, polyester, cotton blended, acrylic, 100% polyester, and polyamide. And we will do a comparative analysis how the microfiber release of microfiber is depend on the composition. And we will also focus how different finishing treatment has an effect in the release of microfiber amount. And we will do further result experimental analysis on the filter paper surface by using scanning electron microscope and FTIR. And we will do also biological oxygen demand and COD test of the discharge water to measure the environmental load from this aquatic microfiber release. So please go to next. And I like to mention so far we have found that huge amount of microfiber is releasing during domestic washing, and the amount of release of cotton is much higher than polyester, and microfiber release decreases with the increase of wash cycle. I like to thank to the Bangladesh University of Textiles to fund this project. And that's all from our side. Thank you for listening. If you have any question, we are here to respond. Thank you.
Thank you, Ms. Humaira, and thank you, Mr. Tanveer, for sharing the outcome of your work so far on this important topic of microplastic and microfiber release. This session and this one was also very interesting, I think, from the perspective of regional cooperation. As you would know, that there is already a test method, an AATCC test method for microfiber release. There is research activity going on in Europe with regards to quantifying and evaluating the microplastics after textile washing. There's work going on an ISO method. There's the microfiber consortium standard. So it would be very interesting if Ms. Humaira, you and Mr. Tanveer could benchmark your work against those existing methods. Very, very useful. Now, the final session of this important aspect of waste management will be addressed by Dr. K.V. Emmanuel. Dr. K.V. Emmanuel is the Executive Director at Indian Leather Industry Foundation. He's credited with setup of over 450 wastewater management plants in over 40 countries, and he's shared his work via over 100 technical papers. So, Dr. Emmanuel, if you can share your many decades of experience and especially your focus on Mbbr, membrane bioreactor for textile effluent treatment in about 12 to 15 minutes, I think everybody would get some insights and then can follow up with you. Dr. Emmanuel, over to you.
Good afternoon, Rakesh. Nice to see you again. Now let us come to this topic. Before we start, I would like to just give you a kind of a background of this. Is that generally, you know, all these symposiums, we focus on our research product outputs to be given to the field. Initially, also when this opportunity was given to me, I thought I would present, let's say, a research paper on the various membrane, RO membrane selections with the technical details. But then I saw that unless the other recipients are also working deeply into this field, it may not be much informative to them anymore. So for a change, I have decided to keep the other way around. Here, I would like to offer some information from the field to the universities to say what's happening in the field so that they could shape up their research activities according to this requirement. Okay, next slide, please. So I'll give you an overview of whatever is there in this thing. Much of this information is known to you, but I would like to keep it summarized so that you get a perspective. Now, if you look at the pollutants in textile effluents, we have got different types, starting with the organics, which essentially gives the color and others, and then the salt, the suspended particles, and then of course heavy metal and hazardous substances, and color and temperature. These are caused by the different chemicals which we are using and residuals of the raw material. Next slide, please. So what is the treatment we are doing at the moment? Everywhere in the region also, we follow the same international practice. Mostly it is with the preliminary treatment, which gives screening, grit removal, and equalization. And then there is often there is a primary treatment using coagulation, flocculation, and sedimentation or flotation. And then there is a secondary treatment which removes organics using microorganisms, mostly bacteria. And in many cases, we have got a tertiary polishing. And in some cases, the recovery and reuse using ZLD units. Next slide. So this is a typical flowchart of a composite textile CATP. Like it gets into a kind of a collection tank, then goes to a screen, and then it is pumped to an equalization tank. Then it is taken to a flash mixer where the ferrous sulfate, lime, and polyelectrolytes are added. And then it goes to, after flocculation, it goes to a sedimentation tank. And the primary treated effluent often goes to the secondary. In many ATPs, we even take out the primary altogether. I have got only all biological treatment also. And the biological treatment is essentially with aeration. With the diffused aeration is the most common thing. And the aerated effluent with the microorganisms goes to the secondary clarifier, where the sludge is settled and sent back to the aeration tank. And the treated effluent is discharged with or without tertiary treatment. And the sludge, which is collected in the primary and secondary, is taken to a thickener and then it is either dewatered in a sludge drying bed or a filter press. This is the typical effluent treatment scheme. Next slide. So to give an overview of what is the issue of this textile effluent treatment as of now, what we are having. One is the space. In many countries, especially in Bangladesh, we don't have much space within the factories. So these ETPs occupy a lot of space. And in many small factories also where it is existing in clusters, the space issue is a major thing. So that is one of the issue. Second is the compact systems. When we have like a primary ETP alone, it generates a lot of sludge, which in turn needs further space. And the clarity of effluent, for common man, the pollution from any industry is color and smell. So the clarity as well as the color of the effluent becomes an aesthetic issue. And any upsets in the biological ETP generates issues like sludge bulking, which makes the effluent comes out as turbid. So this is a common issue. And recovery and reuse is now the hot topic. And there the conventional ETP may need extensive pre-treatment. And many of the organics in the textile ETP is quite complex. Now, I would say that when we talk about organics in textile effluent, many people simplify it saying that, okay, what is there? It's not that problematic. Now, okay, let's have a look at that one in the next slide. Now, you see, these are the kind of organics we have. You could see the number itself is so much. You could see there are different types. There are medium organic load, but with difficult to degrade, and high organic load also difficult to degrade, which is basically from the dyes and brightness fibers, and moderate to high organic, but can be readily degraded, like wool grease or the sizing agents like PVA or starch, and low organic load, but very difficult to degrade, including formaldehyde and chlorinated solvents and all, this kind of thing. Essentially, you could see so many of organic compounds which are really difficult to handle. Next slide, please. So what are the efforts being made to address these issues? Now, recently, many advanced biological treatment systems came up into the field and being used in the effluent treatment of these countries. And the common choice is Mbbr, which is a modification of the conventional activated sludge treatment, or a fluidized aerobic bed reactor, or units such as sequential batch reactors or rotating biological contactors. These units are now becoming increasingly popular. Now, these units consume lesser space and better treatment, but still issues such as space is an issue. And the pre-treatment requirement for recycling is still a major issue. And these all units produce a lot of sludge, which needs to be handled. And Mbbr is considered as an alternative biological treatment for considering these limitations. Next slide. So when you look at Mbbr as a solution, it is a modified biological treatment which uses the same activated sludge. And membranes, as you know, is fine filters which can filter out all suspended solids and colloidal solids. And depending on the pore size, it can even remove dissolved solids when it is nano and RO. And the Mbbr consumes much less space, and effluent is of much clear and less turbidity. And then since it is having very high solids retention, it can treat the complex organics much better. And it does not need much operational issues such as the sludge bulking and all. And it produces comparatively less sludge and needs lesser pre-treatment, because the output of Mbbr you can, many cases, straight away taken to RO without any pre-treatment. Next slide. Now, Mbbr is basically, as I mentioned, is an activated sludge treatment, except that instead of a secondary settling tank, we separate it using a microfiltration or an ultrafiltration. So there is no limitation with respect to the settling characteristic, because there is no settling involved. And Mbbr, it has been developed in the late 60s, but it was not popular till the end of 70s and 80s. Then submerged Mbbr was the game changer. Next slide. And submerged Mbbr uses less power, but there was an issue of the frequent clogging. And the external Mbbr was supposed to be a solution for that one, which is called side stream, and which is being used in most of the Mbbrs today, but it consumes more power. Next slide, please. Now, this is just a kind of visual comparison between the conventional and the Mbbr. You could see in the first picture, you have the conventional treatment with the 2 aeration tanks, and then the secondary settling tank with the sludge recycling. And in Mbbr, you have got a much smaller aeration tank and the membranes placed inside. So you could see the size is much less, sometimes less than half. Next slide. Now, this is the placement of membrane which you could do. The membrane can be made as a cartridge and put it into the aeration tank, or it can be placed outside. And you could see the water along with the MLSS get filtered and comes out as clean water. Next slide, please. So the placement of Mbbr is, there are 2 components. In the submerged Mbbr, the membranes are installed within the tank itself. In side stream, it is taken outside, and the filtered clear effluent is discharged. It can be either pumped out or using a vacuum, it can be sucked out. And the modification of side Mbbr is called airlift, where there is a additional backwash is provided by covering by air. Next slide. So this is the picture of the submerged Mbbr cartridge. You can make it as a cassette and then put it into the tank. And in submerged Mbbr, it is mostly sucked out using vacuum. And airflow in this is calculated for the 2 purposes. One is the aeration purpose in the aeration tank. Second is to scour and clean the membrane cartridges which are placed inside the aeration tank. Next slide. So if you look at the performance of Mbbr versus the conventional treatment, Mbbr effluent has got some, theoretically it should have 0 suspended solids because the pore size of the membranes are much less than the suspended solids itself. So it should have, outlet should have 0 suspended solids. In practice, you can get, let's say, less than 5 ppm suspended solids. The turbidity is also supposed to be less than 10 NTU. In many cases, you may even get it less than 5 NTU, which is the requirement of the RO membrane. Since only dissolved organics escape the system, the BOD and COD reduction could be 40 to 60% better than conventional. And the MCRT, that is the mean cell retention time in Mbbr, can be 80 to 120 days. It need not be always that much, but against the 25 to 30 days in conventional. This ensures the complex organics can be degraded much better. And overall space requirement, if you calculate, it will be about 60% of the conventional ATP. And sludge production from this unit can be 30 to 45% less than the conventional treatment. Next slide. And MLSS levels in Mbbr can be much higher than the conventional. Usually, it can be up to something like, let's say, 25 to 30,000 milligram per liter. But usually, we keep it between 10,000 to 15,000. That is 1 to 1.5% of MLSS. Submerged Mbbr can also be in 2 ways, where the membrane cartridges put it in the same aeration tank or in a separate compartments. And it consumes lesser power compared to side stream. Side stream consumes about 2 to 4, and submerged Mbbr usually take only 0.5 kilowatt hour per cubic meter. Next slide. Now, this is, I already mentioned this one. Next slide. So operating conditions, usually the sludge retention time is much higher. SRT can be 30 to 50 days. This is different from MCRT. And higher SRT is definitely possible, but that will increase the fouling. And the fouling of membrane is usually by the MLSS particle itself, and then the colloidal solids, which is a major concern. Now, once the fouling increases, the flow drops, and then you need to do the cleaning. And the flux rates, when it goes down less than something like 60% of the design value, we used to do the cleaning. Next slide. there are two operating conditions. One is by keeping the pumping pressure constant and then taking the varying permeate flow. And the second one is keep the permeate flow constant by changing the pressure. Now, in our plants, we found that the second option is much better, where you get a steady effluent flow, even though the pressure varies. The Mbbr performance is generally better at higher temperature up to 45 degrees, but beyond 45 degrees, the biological treatment gets affected. So it's not good. And lower temperature also increases the operating pressure because of the higher viscosity at a lower temperature. Next slide, please. Now, the fouling control, generally we use membrane backwashing. There are three types of membrane the cleanings which are done. One is the CEB, chemically enhanced backwash, and then CIP, the clean in process, that is maintenance cleaning, which is done usually once in a week or so. And intensive chemical cleaning, that is to take out all the membranes, clean it extensively and put it back, which is done in maybe once or twice in a year. Next slide. So let's have a look at what are the advantages of Mbbr. Better removal of BOD, COD, and better degradation of complex organics and oil and grease, and a higher SRT is possible there. With the no suspended solids, the treated effluent is much clearer and much less turbid, and lesser pre-treatment is required when it is taken for RO or recycling, and it, of course, much area compared to conventional. Next slide. So the disadvantage is something which I would like my fellow researchers to have a look at it, because this is going to be the future. When we talk about ZLD or effluent recycle as a future, Mbbr has got a high role there to play. So I would urge my fellow researchers, please keep a look at this one, how we can make these disadvantages into an advantage in future researches. First is, of course, the higher capital cost, which is being tried at various levels to bring down the cost by the manufacturers, and higher O&M cost because of the additional power. Instead of aeration power alone, we need also the power to drive the membranes, which is also being researched extensively, especially in Israel and in ITRI in Taiwan and US EPA in US. They are all working very hard to find out membranes which is having lesser cleaning with giving additional coating of polysulfones or polyamide coatings, and then find out repulsive membranes to organics. Let's see the outcome, and let's also work towards whatever we can do it in our universities. Now, the system complexity is still an issue which we need to work on, and membrane replacement, the life of membrane is still a concern. We need to replace the membrane generally once in 2 to 3 years, even though we expect it to be something like 4 to 5 years. Today, the membrane life is not so good, so we need to work on it. And improper solids control in the inlet is something which we need to still work out to make better pre-treatment for Mbbr, to make the Mbbr performance itself better. Now, next slides. Now, let me conclude my presentation by keeping it as an overview. This is a overview is that conventional effluent treatment is generally effective when you talk about the present standards. Now, the future standard, especially when you talk about recovery, the present treatment is not at all enough. We need to work on new treatments, and there are issues like the organics remaining in the effluent, fouling the RO membranes. So we need to have good pre-treatment for the ZLDs, and Mbbr can be an effective solution provided we address these issues, which I already flagged. And system is still under development with respect to power consumption, which I already mentioned. And given the advantage which we have narrated, Mbbr can be an effective unit or a replacement or a modification of conventional treatment for countries like Bangladesh. And it is the same for countries like India or Pakistan or Vietnam and all. Thank you so much.
Thank you, Dr. Emmanuel. Thank you for being right on time. Thank you for giving us an insights into what you have tried out, and also giving a clear call to action so that students and researchers could consider working on those aspects. Thank you very much. Now,
all these washing steps are counter-current washing, and that's why we can reduce it to 3 to 4 or 5 liters per kilogram for each of the washing process. But even then, we can reuse some of other washing waters, which I show you in a minute. And that you see here, for instance, here you see on the bottom, you see on the right-hand side, the chamber 11, and you see also the word neutralization. So this water for neutralization, you can directly reuse. You just have to remove the fibers with a fiber filter, which is a standard operation, and you can then reuse this water directly for desizing. You see the orange arrow back to chamber 3 of the desizing washing, and then it flows from chamber 3 to chamber 2 and to chamber 1, and then it comes out with a red arrow on the left-hand side as the desizing liquor. So that is one option. You can also use what you see here. Then you see here 4 machines. On the top you have mercerization, on the bottom you have a mercerization, and in the middle you have the second one is a combined scouring bleaching range, and on the third one is desizing, scouring, bleaching, what I have shown you right now. And if you have very often cotton fabric finishers, they have also mercerization plants, and from there you can reuse the washing water then for instance, for desizing, or also for scouring washing. And that is indicated here. I don't have the time to explain that in detail, but as I told you, if you are interested, if I have stimulated, you can read the document which will be available for you. So if you have then reduced the water consumption that heavily, then of course you have also the wastewater is minimized, the liters per kilogram. That means it is very high concentrated. And here you see a sample of a desizing liquor, and which is 30 to 7% of the overall COD of the whole company just is in this wastewater. And then another example is exhaust dyeing for cotton knitwear, that you know these exhaust dyeing machines, which you see here left and right. Here you have 2 schemes from 2 suppliers. And oh, can you still see, because we have another problem? Okay, then you yes. See, you can see the samples here.
Yes.
Okay, good, thank you. Just that I'm sure that you can follow. And then you have here you have the different samples from the exhausted dye bus until the 4th wash on the right-hand side. They put that like the traffic here from right to left, and not from right to left as we do it. And of course, then, for instance, the wash number 3 and 4 can be easily recycled for instance, for the first wash. But of course, you need an intermediate tank, and you need to remove just the fibers. And the second is that you use low liquoration machines, and that means liquoration machines 1 to 3, 1 to 4. And then you can also, in this case, you can save the number of bars, and you can reduce that to 4 or 5 bars only, which they do a lot in Bangladesh. And the latest record I heard that they have a full treatment with pre-treatment and dyeing with specific water consumption of 26 liters per kilogram for exhaust dyeing is incredibly low. So I have to look for the time. You see also from the composition of the different bars that you have even factor 100 difference for color, for COD, for BOD, for TDS. And you can segregate the washing at the machine, the washing water at the machine, to segregate it and to recycle the low-loaded washing machine and low-loaded washing water. I have to be not too fast. And for rotary printing, it is important that the blanket washing is only carried out when the machine is printing. Very often the washing, if the printing stops and they the washing of the blanket continues, and then we lose water. All of these techniques are in practice, they are available, but everybody who wants to implement it, of course, has to work on it. And the famous saying from Thomas Edison, there is no substitute for hard work, is also in our field, that we have to really work hard, but it is possible, and we have so many options. And I hope that I could give you a short introduction to water efficiency and very real and practice-oriented techniques. Thank you very much.
Thank you, Dr. Schönberger, for that concise and comprehensive overview of what's out there in the world of water efficiency. We will look forward to receiving a link to the knowledge product you mentioned, and then also share it with all the participants for them to try out.
Yeah.
Now, taking this further, you mentioned water efficiency and energy efficiency go hand in hand. So that's a perfect segue to now invite our colleague, Mr. Salman Butt, who will share with us a little bit more about what's happening in the world of energy efficiency and renewable energy for the textile sector. Salman is an expert on cleaner production, on decarbonization and sustainability aspects. In addition to being the executive director for Aspire Consult in Pakistan, he's also the chair of PremaNet, which, as some of you will know, is this global network of experts. Now, there's a study that Salman was taking care of concerning replacing fossil fuel-based thermal generation with renewable fuel for the textile sector. This was commissioned on behalf of GIZ Fabric and H&M. And Salman will be sharing with us in the next 15 minutes the many months of work they had on this. Yeah. All right. So it's over to you, Salman, then.
Yes, thank you very much, Rakesh, and warm welcome to everybody. Really happy to be here sharing some work that we've done. And a little bit of correction, I will not be sharing the study itself. I will be sharing the link of the study, a little bit of introduction at the end. In the beginning, what I will do is I will build a context of why energy efficiency or energy management is actually becoming is coming into limelight of targets of brands and various international organizations and bodies, and why it is becoming part of the legislation now. So I'll build some context there. And do you see the slides moving first? I need to confirm. Do you see my second slide?
Yes. Yes.
Okay.
Yes,
Yeah. So I will build the context of energy and climate action for textile sector. Then we'll look at different aspects at factory level. What kind of areas of intervention are there generally in the factories when it comes to energy efficiency, energy management? How do we put it into a framework rather than just taking it as an ad hoc measure? We'll briefly discuss a business case of energy management of a factory that improved a lot. And we'll talk about different initiatives on energy and climate by GIZ, including the study that you talked about. So there will be an introduction to that study as well. And there will be few links as well at the end that can be shared. Even those links are in the presentation and that can also be shared. Yeah, so this business perspective of any sustainability measure, including energy efficiency, energy management, is that the company is not actually working in isolation in an environment. So this environment is closely tied together with many global issues, but also with many organizational issues and national and regional issues as well. So there are certain global issues which affect national laws, international agreements as well. There are certain global issues which translate into codes and standards and product specifications, ultimately transform into customer requirements. And there are also pressures of staying profitable and staying in business, which are also then linked to societal expectations as well. So how do you perform in an environment where society is also getting affected by business operations? I'll give some examples of these going forward. So, for example, there are certain international agreements, including Paris Agreement or other such agreements, which transform into national determined contributions or global climate targets, these then transform into legal requirements in the countries. So the countries who have signed up for nationally determined contributions and they have determined their contributions would actually then have to transform these into their national laws or national regulations, which then put pressures on the companies to improve their energy performance, their environmental performance, and they reduce their emissions. Even if in certain cases this pressure is not enormous, but there are other than actors whose pressure becomes more significant. So these are end user expectations or clients who are becoming more and more aware that when it comes to sustainability, energy and climate action are also very important aspects to consider here. So the brands are developing their supply chain emission goals, targets, and these they are transforming into codes of conduct as well. The end users have now more information about the energy sources, and they are requiring for more information as well. So the brands are using different portals or different tools like HIG facility environment module is one of the tools being used where they're requiring more information on the energy sources the companies are putting in, which then convert into again pressure on the company, which the company has to deal with, even if they're not at the moment feeling much pressure on the legal aspects. Along with that, staying in business, reducing internal costs, and having productive workforce are also very important, which also impact ultimately the market situation as well. So these customer demands, end user demands, and societal demands, these transform into sectoral codes and then transform into national legislation, and then all these pressures are coming onto companies. Earlier, these pressures were only related to the air emissions when we go a few years back, but now these pressures are also related to carbon emissions and also other hazardous discharges, or generally intaking which are you really taking in clean energy or not. I will give few references here of different climate conventions or agreements. Paris Agreement, we already talked about, gave an example earlier. The goal was to limit the global warming to well below 2 degrees Celsius, or preferably to 1.5 degrees Celsius compared to pre-industrial levels. But there was earlier a Kyoto Protocol as well, where the clean development mechanism or these kind of things evolved. And even before that was an Earth Summit in Rio in 1992, where energy was not the main agenda, but it was referred in multiple chapters. So you can see how it has transformed as not being the main agenda and now becoming the main agenda in the global perspective. And then there are different other references which are also causing pressures to companies, exporting companies, especially textile companies. There are different non-government initiatives, for example, Greenpeace, who started off working on hazardous waste and water pollution, but now they are lobbying for 100% renewable energy adoption. There are different ISO standards dealing with energy management, energy auditing, energy efficiency. And then there are industry initiatives like the Sustainable Apparel Coalition, using the HIG facility environment module and then requiring companies to report on their energy and greenhouse gas emissions. I will not go into the detail of this because of the lack of time and since we are a little bit behind time, but Sustainable Apparel Coalition is definitely taking the lead in energy as well as other environmental topics. And then Partnership for Sustainable Textile is working with 150 other representatives in different sectors, especially in textile sector. It is being led by GIZ. And then there is United Nations Framework Convention on Climate Change, where this nationally determined contributions are being monitored. And then Intergovernment Panel on Climate Change is actively monitoring emissions, actively generating guidelines. And this was a report from IPCC, which was a famous report which told everybody that this target of 1.5 degrees is more likely going to going to go past 1.5 degrees of global warming quite early, as we thought, from what we thought earlier. And there are different ISO standards. ISO started off with ISO 50001 being an umbrella standard for energy management system, but there have been many more standards, links to which are given here, which deal with the energy savings, which deal with the energy performance monitoring, building environmental design, but also going deeper into energy auditing or compressed air energy assessments. And there are many more standards on energy which are being developed by ISO. So this framework, so what I wanted to say was that energy or energy management or climate actions or climate targets are not something that are now being seen as an individual standalone topic to be worked upon, but this is now linked with all the sustainability topics that the companies have to work upon, and on which the brands are requiring companies to work on, energy efficiency being one of these. When it comes to resource efficiency, we're talking about reducing energy use or maximizing the use of renewables or alternative energy sources, reducing dependence on fossil fuels. But then it also supports in emission reduction. You can see the blue columns, talking about controlling the environmental flow or reducing the environmental flows or reducing carbon emissions, or even transforming into improving management practices to ensure that all these measures that are being taken on the left hand side in resource efficiency or emission reduction are then sustainable as well. So this framework was developed by RMIT University in Australia. It can be used as a reference framework to see how these topics are interlinked and not to be taken in silo. So what to look at factory level when we're talking about energy management? You can see there are different aspects at input, at as well as in process as well as output side. At input side, you can see the company has energy supplies. There could be grid emissions there. Then there are fuel supplies where fossil fuel is coming in, or if there are non-renewable energy being purchased, for example, or this would have contribution to the greenhouse gas emissions. Inside the factory, the process or processing is being done where there could be inefficient combustions. There could be emissions to air in terms of waste heat, in terms of carbon dioxide, methane, nitrous oxide, or other pollutants could be going out, which then get deposited if they're heavy, or if there's a rain, for example, they get deposited into soil. And there are process or material wastes that are going out, and if product is going out, the emissions would be in the transportation as well. If there are waste going out, or if they are going to landfill, or if these wastes are going to incineration, even then there would be emissions to air or pollutants to water and soil. And wastewater which goes out, if wastewater heat is not being recovered, it would contain heat, obviously. That means energy is going out. And if there are solid fuel ash residues or liquid fuel spills which are also going out with wastewater, these would add to the pollution. And when it goes to when the whole wastewater goes to effluent treatment plants, there would be emissions in treatment as well. So all these aspects of emissions which are covered under scope 1 or scope 2 or scope 3 emissions need to be looked at when dealing with factories, when working in factories on the energy management or energy efficiency or climate side. So not only to look at the point source emissions, but also one has to look at all these aspects which are not sometimes directly related to point source emissions or inefficient combustions. So what can be done? So at the input side, how the issues can be addressed. So input side, the factories have to look at energy security. They also have to look at energy cost, but also have to ensure that the energy that they're getting is clean energy. But when it comes to process side, the factories have to improve awareness among the workers. They have to put in certain process controls. They have to show leadership, because if the leadership is not shown, obviously nothing can sustain. There could be ad hoc measures, but then the measures cannot sustain. And also very important is energy efficient procurement and design. So are the factories really procuring materials or procuring equipment or machinery which are energy efficient, which are water efficient, or if they are designing the facilities to become more energy efficient in future, if are they analyzing and reducing the wastages or non-product outputs. And when it comes to output side, if the product is going out, obviously the customers would have their own requirements of related to the product quality, or if there is incineration, for example, of the waste with being done with energy recovery or not, or if your wastes are being diverted away from incineration without energy recovery or not, if the waste is being upcycled or not. Waste heat recovery from the wastewater, or waste heat recovery from the waste air, emission control equipment to be installed, which obviously then leads to legal compliance as well. So all these aspects are to be addressed in the company when working on energy management. As you can see, that not only the process aspects, but also input as well as output and waste side has to be addressed in the company. So unless a holistic approach is used to address all these issues, whatever actions are taken in the companies on this front of energy efficiency or energy management, they might not sustain for longer run, or they might not provide the results as were told in the as I depicted in the earlier slides, how all this is transforming into then brand requirements or the legal requirements. So to address all these, company has to address all these internal as well as input and output side issues as well. So what can companies expect? So maintaining a license to operate is one of the possible outcomes. That means if you are working in an area where you are where your energy combustion sources for combustion point, for example, are not really efficient, it not only causes you energy loss, but that also means there would be more pollutants to discharge, and then it might have legal implications. But access to global markets, if you are performing well, if a company is able to show good performance in environmental environmental emission reductions, for example, or greenhouse gas emission reductions, they can have better access to global markets. They can maintain competitive edge, and also they can try to reduce repetitive changes to energy mix if they can go towards sustainable energy procurement, if they are able to induct more renewable energy. But also from the business perspective, they're able to reduce cost by reducing energy wastages, and this is a definitely a proven case for energy efficiency. Traceability of energy and greenhouse gas emissions is also improved if you start working in an organized manner on energy efficiency, energy management. But this is not, I don't mean to say that this is a very complex process. Where to start with is what kind of inputs are coming to the processes, what kind of processes we are doing. These are the starting points. And what kind of outputs are we getting out of it? Are there any wastages going out? Are there any, what is the desired final product? When it comes to desired final product, what are the demands of the customer? So if we start addressing these points, what are the inputs of energy, raw material, and water and chemicals, and then how are these processed, and how are these transformed into products and wastes? If we start with this, do a scoping, that is where our work on energy efficiency starts, and then we can slowly and gradually work on other aspects as well. Case of one textile company I would like to present here. This one textile company which went through energy and water project under Clean by Design initiative of Apparel Impact Institute, who were able to save 7.5% of water input. They were able to reduce energy input by 3.6%, and also were able to reduce their emissions by 2.9%. The investment that they made was only around 0.1 million USD, and the savings they were able to make were 0.33 million USD. This you can see with a payback of only 4 months. And this included not only no cost, low cost measures, they also invested in improving their waste heat recovery, improving the recovery from processes. So they installed a lot of wastewater heat recovery projects as well. Along with that, they were able to work on improving their combustion efficiency. So usually the companies which we've seen working on these topics, on the right hand side, you can see I've presented some of the measures that companies work upon. And some of these can also transform, some of these also require research as well. So for example, talking about improving combustion efficiency, so exhaust monitoring and automation is also something, also one of the measures. But improving the fuel calorific value is also very important. So by briquetting or moisture control, this is something where universities can also do the research work. And then coming towards network improvement of way of steam network, for example, or thermal oil network, for example, where better heat exchanger materials are required in the companies. So companies are trying day by day to have better heat exchanger materials which don't leak a lot, but also that don't cause too much noise and also exchange heat very efficiently. Recently, factories have been shifting from conventional iron or cast iron to or conventional steel to stainless steel, but that increases noise in the factories when the steam or compressor is passed through. So this is something that also universities could work upon when it comes to research work or when improving this the efficiency in the companies. Then process parameter optimization is an area where research work is required. There are more innovative technologies coming in. We've seen lately a lot of machines, especially washing machines, which consume lesser water and lesser energy now. But much more research needs to be done in this area, so that same processing or more products can be produced with lesser energy inputs. I would like to present few initiatives on this by GIZ, as Rakesh mentioned earlier. So one initiative is the climate action training, which some of you might have already attended. So this was developed in cooperation with GIZ Fabric and UN Fashion Industry Charter for Climate Action and 10 other brands and manufacturers. This training is available at atingi.org. If you go at atingi.org, you can find this climate action training there. It's available in English, Mandarin, Khmer, Bengali, and Vietnamese at the moment. Then there is another training program developed, that is resource efficient management of energy. It is also developed under the GIZ Fabric by Aspire Consult in consortium with TÜV Rheinland, Adelphi Consult, and some other partners. And the goal is to equip the energy service providers so that they are able to provide services to factories in a more sustainable way, and they're able to guide the textile and garment factories in achieving sustainability, not only improving the efficiencies as ad hoc, but also to do it sustainably. Then there are two parts of it. One is the master trainer program, which was conducted as a live web training of service providers in 2021. And the phase 2 of this we are taking up as practical application in 2 factories. So these service providers which were trained will now conduct energy efficiency assessments and energy audits of factories in Vietnam under the supervision of master trainer, and then the implementation phase starts. Another initiative in this would be training of energy managers of the factories, which is coming up in June or July. The recorded lectures and training material is being uploaded pretty soon. We're working on improving the quality of the videos and also inserting subtitles in the recorded lectures. These will be uploaded on VCOM as well as Asia Garment Hub websites. And at the moment will be available, the material will be available in English and Vietnamese. And then this study that Rakesh, you want to say something? Sorry.
No, please go ahead.
Okay, I think it's the last slide anyways. Then there was this study that Rakesh mentioned earlier on evaluating renewable thermal energy options for textile and garment sectors in Bangladesh and Pakistan, which was conducted with support from H&M, Aspire, Adelphi, and Reed Consulting in Bangladesh and Pakistan. And the objective was to identify the potentials where greenhouse gas emissions can be reduced in textile and garment sectors, focusing especially on renewable thermal energy. In this, we evaluated biomass for steam generation, including combustion and gasification, as well as solar water heating. And it was the evaluation was not only on the technical aspects of it, but also on the commercial aspects of it. So we had a detailed look at if the biomass is available and what kind of biomass is available, and is it available in enough quantities that a transformation from coal or natural gas towards biomass can be done. And then also looking at the market of solar water heating, comparing it with solar photovoltaic, although these cannot be directly compared because one is producing thermal energy and one is producing electrical energy. However, they are consuming the rooftop space. And then we wanted to compare which one makes more sense for the companies who also have thermal energy demand. Should they go for a mix of it? Should they go for water heaters, or should they go for solar photovoltaics? So this study is available at this link. This is inserted in the presentation as well. Probably if somebody could also copy this link in the chat, so that others can download this.
We will.
Thanks. So this is what I wanted to present, just an overview of why to work on energy management, but not only why, but why to work on it in a cooperative and collaborative manner, with looking this in conjunction with other topics of environmental management. And these are some of the references which you can access.
Okay. Thank you very much, Salman, for starting off with that big picture on international conventions and then going a little deeper onto industry level, factory level. Now let's go a little more deeper then with Dr. Abbas, where Dr. Abbas and his team have looked at a particular machinery, in this case, the specific energy consumption of flatbed knitting machines. And he will share with us how information was captured and recorded with loggers on energy consumption and some recommendations for us from there. Dr. Abbas, as you know, is the head of department for chemical engineering, but he's also active in several global projects and initiatives. And in addition to being an academic professor, he's also a practitioner. So Dr. Abbas, it's over to you. If in 15 minutes you can take us through your work, would be great.
Thank you, Rakesh, sorry. Let me share the screen first. Just give me a sec.
Mm-hmm.
Okay, so it's all right. All right. Thank you very much, Rakesh. This is a very specific work. Often we face problem in the when we want to work with machines. How do you know that a machine is energy efficient? Where is the industrial benchmark? We face it for everything, like we face it for water, we face it for material, we face it for energy, we face it for chemicals, we face it for also air emission. That where is the benchmark that from there we can consider that this particular machine is energy efficient or not. And to that context, we have studied this particular a specific energy consumption of various flatbed knitting machine. I have Philip Proctor and Abdullah Mamoon along with me on this, task. So before moving into, what I'm going to say is, background, there will be methodology, the results, and the comparison and conclusion. Now, what we studied is, this is a flatbed knitting machine from different factories. These are the machines that has been used particularly in the sweater industry. And you can see that there are 5 particular machines that we've studied. 3 is from China, 1 is from Germany, and 1 is from Japan. And these machines are very popular in Bangladesh, and especially if we know that the sweater, if you look into the sweater industry, even 5 to 8 years back, the sweater industry has been dependent totally on the humans. So it is actually manual operation with the knitting to linking to dialing to everything. However, due to various issues, the entrepreneurs has been moved into the automated machines. And since then, the exponential growth of sweater factory has been foreseen, which also tells us 2 stories. First is the production got higher with less number of workers, and also how, because it's now machine dependent, so we rely on power and how the machine can be energy efficient. And this is a very challenging task in some context. I mean, I will discuss it in our session. So what we measured is a specific energy consumption, which could be defined as the unit weight of product, the energy consumed by the unit weight of product, and which is expressed in kilowatt hour per gram or per kg fabric produced. So what we did, our methodology is, we went to the factory, we looked into the different parts of the factory. That is, for us, it has to be one single product, including front pieces, including back pieces, the overall product, so that we can compare the specific energy consumption. So you see the front piece and the back piece, and after the front finishing of the front pieces. After that, what we did is basically we weigh the front part, back part, 2 sleeves, and then what we did is we did the weight of the back part, weight of the front part, weight of the sleeves individually, and the weight of also the total finished pieces. So that way it gives us the total weight of the garment that is produced by that particular machine. From there, what we did also, that during the production phase of that particular parts or particular full products, we use power logger to measure the energy consumption of that particular product in that particular time. And we use Flux 1735 power logger. And we try to take the power consumption at least once, but I mean twice, to get the production data much more consistent on the result. Now, when we data collected, you see, so the number of samples, and you see the body parts of that weight of that body parts, and then you see how much time it requires. So we made the power log time, and then how much energy is consumed to in watt, and from there you see average operating power has been calculated, watt hour. And then from there, we actually calculated energy per gram of that particular, products. So in that way, you see, to give you an example, that let's say one full product has been taken, it takes around 1.241 watt per gram or equivalent kilowatt hour per kg to produce. That is how we calculated. And from there, we also calculated, although probably not part of this study, but not part of this presentation, is how much greenhouse gas actually emission that we faced. So once we established this methodology, we went to, different machines, different factories and different machines. And there we actually found out, the brand A, that the other thing is also we calculated when the machine has been installed. So for example, if the machine has been installed earlier, likely that over time it will consume more power. So brand A is 12 gauge, and then average operating power we found is 317.2, and energy per gram is equals to 0.893. So brand A, another brand China is 1.42, another brand C China, also it's actually a different gauge, is 0.729, brand C China, brand D and brand E. And from there, we found the industry average is 1.447. That means, let's say to produce a garment, 1.447 kilowatt hour energy would require to produce per kg of, let's say, flat sweater or similar product. And if we look into that from the base, from that baseline of 1.447, something very interesting that the Chinese machine, some Chinese machine has been taken 62% and 50% of the energy compared to maybe other China machines, and also in some cases German and Japan machines as well. So we need to, in this result, we need to assume some of the parts. For example, when we considered that how long, 55 minutes take to one parts, but if we need to annualize it, then we consider 300 days per 10 hours per day with the user factor 78%, and through that we actually made how many grams per hour it can produce, and which is, let's say, 350 grams per hour it can produce by machine. That is an assumption for all individual machine has been taken apart. So I'm giving an example of one machine where it takes 55 minutes. Some other machines would take different types of production time. And here you see, if we compare with all these five different brands, but one with two different gauges, you see a very interesting also production rate. Sometimes when we are considering this machine to machine, we also consider, maybe the machine has been consumed more because the production has been higher. So that is also taken into consideration. And you see different brands production rate gram per minute is 5.9 to 5. So the lowest is 4.0, one China brand, but it's also energy consumption is higher. But similarly, in the Japan and German brand production rate is comparatively lower compared to some of the Chinese brands as well. That is also what we found. But interestingly, this data is very for us also interesting, because we know that some of the German and Japan machines are usually very highly efficient and highly I would say also can produce complex garments. So one of the challenges of that limitation is also when we do the study, because we studied in 5 different factories, not one single factories. So they are not making the same products. Although let's say the weight is the same, but the design, machine gauge, weight of the fabric, and the pattern types are not the same. So which means basically, although we try to establish a baseline for the particular knitting end product, but due to the design parameter or the types of fabric or types of garment variation, it is always difficult. Secondly, what is specific energy consumption we calculate based on different parts and make it as one single garment. So when you did that one garment, actually it doesn't show the whole picture in some cases, because initial stages of the production and the end stages of the production are not the similar. So it is always takes time to initiate the batches. But once the factory the production is running, the machine parameter becomes settled, and it actually takes much comparatively less time. The other issue is the time comparison. You see around 55 minutes or less than an hour to produce a garment, which basically also tells us difficulties, because as I said, we did different pieces to make a garment, not a whole batch or maybe 24 hours or 48 hours to get the let's say represented data as a whole for that batch of that style or that particular design to produce. In that, I mean, if we could do 24 hours or 48 hours, we might have a better representative result. The other point is ambient temperature. Ambient temperature is also key. Some of the machines are with right kind of humidity and also temperature with air condition, but in one or two cases that particular machine is not running is in high temperature. The other point is also the machine breakdown. I would say others say yarn breakdown. So during the production, one or two cases, let's say, although we did it again, however, the yarn breakdown takes place, which needs to be fixed. The other point that actually I haven't added it, although you see in the result in the Japan and German machines are basically let's say low productive compared to the Chinese and Chinese machine. One of the reasons is these German and Japanese machines are basically designed for making a complex product. Sometimes the product that we produce is basically let's say solid garment, basic sweaters, and that is much more productive in case of some kind of very specific machine to that. These Japanese and German machines are designed to produce complex garment, which basically tells us that we could target our machines based on the product that we want to produce. So in conclusion, we did an attempt to set a benchmark for the specific energy consumption in flatbed knitting machines, and an industry benchmark is identified for 5 different manufacturers to understand how much energy is consumed per gram of fabric produced. But further data and further analysis would be required, and as I said, in the limitations, if possible, the representative sample, if possible for the longer time consumption, if it can be measured, then it could give us a very scientific data to before purchasing any machine, particularly in terms of productivity of particular kind of garment, and also the amount of energy consumed in that scenario. So that's it from my end. I think I have completed in 15 minutes. Rakesh?
Perfect. Dr. Abbas, that was perfect. Specific example, concise, comprehensive, and all the best with the next steps of this benchmarking. Very useful to see. Thank you.
Thank you very much.
Now,
thank you.
Right. Now let's take it a step further. We looked at the big picture of energy efficiency. We heard about water earlier. We heard about waste. We heard about the specific case of energy. All of this requires good management practices, good housekeeping practices. So what does good look like? For that, we have with us Dr. Helmut Kruse. He's been working with the German Technical Cooperation Agency since 1975 and has expertise based on work in North Africa and Southeast Asia. While initially he started looking at the topic of water resources management and environmental protection, he has expanded his scope also to Indonesia, Algeria, and Tunisia. He was formerly the head of the sector project for chemical safety for GIZ. And then since 2015, he's been supporting the German textile partnership in the field of chemicals and environmental management. His scope goes beyond chemicals in the area of marine litter, single-use plastic, and water management. And I'm sure based on all he has seen and all he has done, he can tell us what good looked like. So Dr. Kruse, If you can, in the next 15 minutes, share a summary of what you have observed and also some recommendations for the industry concerning good housekeeping for resource efficiency.
Rakesh, I will try my level best. First, you can see my screen and you can hear me.
Yes, perfect.
Okay, thanks. So in the second session, resource efficiency in textile garment, we heard a lot today already about the details and about some specific tools, energy efficiency, and Harald Schönberger talked about special issues of wastewater management, and many of our eminent colleagues has given an overview. Myself, I will focus, as Rakesh said, a little bit on the experience and also go back a little bit to more general aspects of good housekeeping in textile finishing processes. This might sound a little bit old-fashioned, but this is still a tool which is valuable for the general management of or good management of a company. And we heard also about Brebanet. Salman Butt is also a member of it. This was one tool which was introduced by GIZ worldwide and gave a lot of input in the 90s of the last century and also up to date. What is good housekeeping? Good housekeeping refers to a number of practical measures based on common sense that enterprise can undertake immediately and on their own. This, I think, this is important, that this is not a rocket science. You can do a lot of things which are cost saving, which are efficient and are very valuable for your operations of companies. We are here in RUN. This is a regional university network, but why I'm talking about these basic issues, because our students should be exposed to such issues as well and take it then away towards the practice and to the shop floor. Thus is a management tool for cost management, but also environmental management and organizational changes. When these areas are adequately taken into consideration, a triple win, this means economic, environment, and organization, can be achieved, and a successful process of continuous improvement in the company can be established. This means it is not a single event issue, it is a process which we should continue all the time and stay behind. The consequent implementation of good housekeeping can provide the basis for certification according to internationally accepted standards like ISO 14001 or ISO 45001 and the eco-management and audit scheme, the famous EMAS. Good housekeeping practices consider, amongst others, appropriate maintenance and cleaning practices. Maintenance for me is one essential part for a sustainable operation. Many companies are not investing too much in the permanent preventive maintenance of their machinery and processes. Measures to avoid leakage of chemicals and liquors sounds evident, but often we found leaking valves and so on. Avoidance of emissions of untreated wastewater to the environment. Since we saw quite a number of pictures this morning already, so there is still scope for improvement. Monitoring. Harald has mentioned monitoring is a critical issue for the process parameters. Reduction of waste for unavoidable waste and gaseous emissions, but also chemicals management, like correct storage and handling water polluting substances. The chemicals inventories might be an issue which are very relevant and also part of many compliance issues of brands and retailers. And this leads also to occupational health and safety measures, the correct use of personal protective equipment, and we heard already about energy efficiency measures. The benefits of good housekeeping are clear. This keeping work areas neat and orderly, so avoid the risk of accidents, removing waste materials and keep off fire hazards from work areas, paying attention to important details such as the layout of the whole workplace to have a more efficient and operational setup. Good housekeeping is also a basic part of incident and fire prevention. It's an ongoing operation, as I mentioned. It's not a one-time hit and run cleanup, which is done occasionally. It should be always considered and going forward. Seeing the time is running, I will go through. I think the presentations will be shared, and who is interested, he can then also refer to this shared presentations. There are quite a number of benefits of good housekeeping practices. Reduce property damages by improving preventive maintenance. This is, I think, one of the important issues. Lower workers' exposures to hazardous products, and also to more energy, water, and material efficiency. The three benefits of good housekeeping are cost saving, better environmental performance, and organizational improvement. This means you can perhaps save also efforts in the workmanship with a good organization. And so can be seen as a triangle with synergistic effects, allowing companies to tap into triple win options, which can lead to a process of continuous improvement. So a little bit more in detail: reduction, reuse, environmental sound recycling, treatment of waste. We have to monitor the waste quantities and qualities, segregating and collecting waste according to different categories, avoiding and reducing waste, including packaging wastes, reusing waste materials by product back in the company's own production process. Recycling, selling certain wastes in the fractions which are represent the value should be marketed with the waste management scene. Properly disposing of waste that cannot be reused or recycled, separation, handling, and treatment, and elimination of hazardous waste. This is one of the critical points: hazardous waste. Materials should be appropriately stored and handled, as well transported. Again, monitoring the quality of purchased raw materials. The purchase policy should be clear and be designed for every process. Ensuring proper handling and storage of purchased raw materials and manufactured products. Applying the first in, first out principle to avoid the accumulation of obsolete stocks. This is often the problem. Establishing adequate, secure, and controlled storage for hazardous materials, handling dangerous substances with care, properly cleaning and disposing of packaging material, as mentioned. Good chemical management practice. Chemicals handling, labeling, storage, use of chemicals, and chemicals waste handling. These are some of the major issues. The tasks and elements of a good chemicals management practice: purchase policy, as mentioned already, control exposure and releases, select and use personal protective equipment, provide training procedures in instruction, important, improve chemicals handling, always to try get better, safe chemical storage, safe chemical transport, plan and prepare for chemicals emergencies. There should be an emergency plan in case of an accident or a fire. Manage and dispose chemicals waste. Again, the basis for this might be always a chemicals inventory, a well managed and actual chemicals inventory. Documentation required for chemicals of concern. It is exactly that one. Your company is expected to obtain and keep a record of signed and dated declarations like certificates of analysis, COE, test reports from your dye and chemical supplier. Confirms that the formulations supplied to the facilities are conform to the relevant retailers or facilities own restricted substances. Lists the RSL or the ZDHC MRSL, well known and also applied far. So it is, we will skip that one. Reduce the risk of hazardous chemicals can come in contact with the workers and or the environment to the lowest possible level, and consider it could produce fire and explosions. Always better than reducing the risk is eliminating the risk altogether by avoiding or substituting the hazardous chemicals or as an alternative to improve the operation process. The substitution of hazardous chemicals which are banned under RSL or MRSL is a target which GIZ, Fabrics and other projects within the textile cluster of GIZ is always longing for and tried to support. To minimize risks, usually a multi-point strategy of control can be used to prevent and to reduce the possibility and thus the risk of accidents, health impacts, fire or explosions, and adverse effects on the environment. So, some more pictures: improve chemicals handling, transport of chemicals and chemicals waste to, from and within your company, receiving and unloading, the internal transport, conveyance. These are the issues which the chemicals handling are important to take to consider. Here we see some pictures, the bad examples and the better ones. We know them all, the colleagues who are working in facilities and in finishing companies. They know these very well. I hope always the better ones are standard today in the companies you are working with. This is also leading to conserving materials and energy, reducing the volume and toxicity of waste, and there are also economic benefits in the implementation of such measures. These measures usually are relatively easy and often of low-cost nature. This is low-hanging fruits. We should consider that and improve the situation. Often it is a question of awareness as well, training and if we have started to operate in a good way, then often it is the benefits are clear and obvious. So time. Chemical storage. There are some good examples. Ventilation, the floors, the layout are important to consider. Improved chemicals handling. You see here the floors are very wide and you can work with floor handling equipment, and also these are separated. This is a big one, but you can also see that also on smaller bases. I come back to operation and maintenance. Pay attention to equipment maintenance and operations. Here, the picture shows a leaking valve, and often it is very easy and low cost to fix it. But fix it in time and to avoid damages and losses. We should take a closer look at the machinery, pumps, pipework, including abatement systems, well maintained and free of leaks. Regular maintenance schedules should be established, and according staff should be trained and supported. Often these maintenance stuff is at the lower end of our production line, and but this should not be. They have an essential role to play. Again, this is more in detail. So, some possible useful corrective action plans. Actions. Establish purchase policy and practices for the chemical management, improve the chemicals handling and storage, provide training, standard operation procedures and instruction, and perhaps establish a maintenance checklist. These are, in short, some inside views about good housekeeping. I think, in spite it is not very specific, it is a more holistic approach and concept which should be promoted and also inserted in the culture of sustainable textile production. Thank you very much. I'm ready for questions. I have not overrun too much my time, I hope. Rakesh, yes. Tell me.
Yes, it was perfect. Thank you, Dr. Chris. You were perfect. We still have a couple of minutes for questions. So if something pops up, we will direct it towards you. It was useful that you also made a good wrap up and you made the connections to what we heard earlier from Dr. Schoenberger, what we heard earlier from Salman on energy and water. So very good. Thank you for wrapping it up. Thank you for giving us also this guidance, simple but important guidance on how factories can start going in the direction of good or better. Especially the part of training and SOPs is something, as you know, that the Fabric program with capacity building is working on. So it's very useful. Then before we go on to the next session, Emma, now is also time to hear from our participants. So if we can have the poll on screen.
Sure. Yep.
For the participants. And if I can please request all the speakers from this technical session 2 to put on their camera so that we could at least take a virtual picture together. So if colleagues who are presenting during technical session 2, if you could put on your camera momentarily so that we capture a picture. Right, and meanwhile for the participants, if you can please share your feedback via the poll question. How are we doing, Emma? Do we have some feedback already?
Yeah.
Emma? All right. Right, so should we put it up?
Yes. Okay.
All right, let's have a look. Right. So, yeah, as you see, so
So the
thank you
picture
very
thing
much.
is done. Yeah, the picture session is done, right?
Yes, yes, it's done. Thank you.
Thank you.
Yeah. So as you see the results based on your great preparation and delivery of the concept and guidance, you see that our participants considered the inputs and interventions satisfactory and very satisfactory. So we started off looking at the topic of waste. Then we went a little upstream and we looked at resource efficiencies, water, energy, and interventions. Now let's go further upstream at raw materials. And we will start off this third technical session with Dr. Hai. Dr. Hai is with the Hanoi University of Science and Technology. He's the Vice Dean of the School of Textile and Garments. His master's project was on dyeing and printing technology, and he has contributed his work via more than 20 publications. So Dr. Hai, if you could share with us your work on banana fiber pretreatment in about 15 minutes, so that we get to see what kind of innovation is taking place upstream and material level and finishing.
Yeah, thank you, Dr. Chairman. Can you hear me?
Yes, we can hear you well.
Okay. So thank you for spending time to listen to our research. So to come here, I just want to show the very brief of our research now is on banana fiber. So firstly, I would like to share, I come from Hanoi, Vietnam. So Hanoi University of Science and Technology, we have more than 60-year history. And come with Hanoi University of Science and Technology, School of Textile, Leather and Fashion, also start for the very first time of Hanoi University of Technology. So recently we focus on three fields. The first is self-cleaning treatment for cotton fabric by using titanium dioxide. The second is electro spinning of cellulose dissolved in FAT solvent. And the third one is yarn making of banana from banana fiber. This we found that very interesting, and today I would like to show you a brief of this field. So you know, in Vietnam we have very potential of banana fiber. So we have more than 150,000 hectare banana farm and more than 50,000 hectare in home garden. So for the fiber we can collect in everywhere, but of course it's not like a big industry. But we can thinking that, oh, just the banana just only for the fruit. So why we don't collect the fiber and to make a yarn, and further we can do a fabric or something like that. Of course, I found that in India also have fiber making or yarn making for banana, but in Vietnam it's not really good industry. So for the farmer, they just focus, they just they can collect the banana fiber and then making handicraft. I think for handicraft it's okay, but we can go further by making a yarn and fabric. So the advantage of banana fiber, all you know, so it's a natural fiber, have soft and very comfort. The banana can easy to biodegrade, non-toxic, and it has some very good characteristics like water resistant or fire resistant. And of course it can, and I hope the spinning is going very soon in Vietnam. So to do this research, the first one I will see how banana fiber behavior in NOH solution. So for this study, we let the banana fiber in NOH solution 0.5 mole, 1 mole, 1.5, 2, and 2.5 mole. For the time is 5, 10, 15, 20, and up to 30 minutes. And we measure the fiber diameter by microscopy. And we take the photo in 5 minutes, and then we measure the fiber diameter, like in you show. So for the magnification is 100 times. So we can measure the behavior of fiber in NOS. So the result shows that banana fiber not swelling so much in comparison with cotton fiber. So for in water, it's around 0.2 or 0.15 millimeter. In NOS solution, it's just around 0.25 maximum around. To clean or to study on pre-treatment of banana fiber in NOS. So we just treated with NOS in 100 degree temperature in 1 hour. And we see the weight load of the fiber. So for the weight load, we can calculate the lignin, the pectin is get out of the fiber, and we hope that we can see only the cellulose in the fiber. So the weight load, so that's up to 8% of NOS solution. The weight load is around 50%, and then it's very stable. So I think we can stop at 8% of NOS treatment, and this is very good for the next phase. We can go for the scouring of raw banana fiber. To remove the non-cellulose in the banana fiber, so we go for first treatment with sulfuric acid, and then second treatment with NOS. So for treatment for by sulfuric acid, we rinse the raw banana fiber 4 hours in room temperature, and then that fiber go for NOS treatment. And we also compare it with the weight load. So for the weight load, we saw that for 8% of NOS is quite good, and we checking for the tensile strength of the fiber. Of course, for the fiber, we can measure the tensile strength and to see the tensile strength behavior after treatment. So for the tensile strength, the raw material, the raw fiber is quite good. I think more than 500 centinewton per centinewton. But after treatment, it's go down. Yeah, because of the lignin, pectin, and some something else go out of the fiber. So the fiber still reduce the tensile strength in the fiber. So for the further, we hope that we can find the way to determine the spinning ability of the fiber after pre-treatment. So that's all thing that I want to show with you all today, and hope I can get some comment or question for this presentation. Thank you for your attending.
Thank you very much, Dr. Hai. Also, thank you very much for this initial result of your assessment on the fiber. We will be following and interested to see how this topic develops, because as you rightly said, there's an impact also for other countries which have significant banana production.
Thank you.
Thank you for that. Now, let's take it a step further now. Yeah. Do we have Emma, our colleague from Ho Chi Minh University of Technology, Dr. Hong?
Yes, I'm already here.
Okay, perfect. So let's go a little further as Dr. Hong will share with us about this development of an oil absorbent web with dry laid method, yeah, for polypropylene and chemical treated material. So if you can take us through your work in the next 15 minutes or so that we get some insights, it will be valuable. Over to you, Dr. Hong. All right, we can see your presentation now. Right, whenever you are ready.
I'm ready. Sorry. Yeah. Can you see
Perfect.
my
All right.
presentation right now?
Yes, we can.
Okay.
Thank you.
So good afternoon. Thank you very much for giving us a chance to present one part of our work today in our run symposium. Actually, Ho Chi Minh City University of Technology today come with the two presentations. First is about the development of the oil absorbent web by the dry laid method from propylene and chemically treated carbon. And the second is we will talk about the results on the bacterial cellular treatment. So first, I'd like to share first part of our work, and the second, I will introduce my young colleague, Win Harvard, to share the work that has been done in our university. So first, I'd like to talk about the treatment for the carpet fiber. Actually, for all of you, maybe this fiber is not new. In some area, for example, in the Southeast Asia and some other countries, maybe it's a little bit far for the people from the Eastern or from the Western, for example, but for us, it's quite popular in a typical country. And there's already some of the work mentioned about the use of the carpet fiber as an oil absorbent web. But for us, we redo this research because we would like to form it as a matrix or a web for the to replace a polypropylene or mix with propylene fiber to be the oil absorbent web. So the purpose and the methods and reason and conclusion will be included in our presentation today. So as I mentioned about the K-pop, it's quite famous for its oleophilic properties. Anyway, there's a weak point of it is the mechanical properties and the morphology, because it's not easy to form the web with the K-pop. It's a hollow fiber and it's also quite lateral, and it's not easy to be mechanical join with each other to form web or yarn or whatever. Therefore, our study tried to demonstrate the process of creating a web from the blend of treated K-pop fiber and also the propylene fiber to be the oil absorbent material. So our process is we collect the fruit, of course, from the trees, and then we separate from the dry fruit, and then we blending with different ratios of K-pop and also propylene fiber with different ratio, and also we feed the fiber plant to the laboratory carding machine, because with this carding machine we can mechanically form a web, and then we consolidate anti-desiccing using the heat press and other technique. And the absorbent behavior of the formed web we evaluated by the according to the standards ASTM 726. And here's the figure out of the step that we already done with the K-pop fiber. After that, we did the pre-treatment, and we use treat with in 1 hour in 30 degrees with the concentration of acid and with different concentration as we saw in the figure. And we try the oil retention or oil absorbency with different oil like diesel, kerosene, and also vegetable oil. That is a popular oil using in our life and also in the industry. After this pre-treatment, we also can we show the diagram of the oil absorbency of 1% of acids and treated cable fiber for 1 hour, and this we try with different temperature. So all the work is here is we already try with different technical parameter of the treated fiber and also the other condition. And in figure 3, we show the absorbent web that already formed from our laboratory cutting machine and also with different blend ratio. And here we consider about the tensile strength and the innovation of the web with the different ratio. And we can see in the figure that the tensile strength and also the erosion of the web is acceptable for using in our laboratory condition and also maybe in the temperatures and the other weather condition outside. To have the close look in the structure of the fiber and the web, we already took the SEM photo, and here we can see also the orientation and the alignment of the cable fiber and also propylene fiber mixed in the oil absorbent web that already formed from our laboratory cutting machines. And one of the things we would like to emphasize here is also the oil absorption or oil retention, and also about the removal the oil from the fiber. And we try to demonstrate it by the contact angle. Here's the photo. Already tried to show you about the contact angle between the absorbent web and also the water. We try to drop a drop of water here and we measure the contact angle. And this the image of a droplet of the oil that penetrate in the open contact with the oil absorbent web. We see very clearly in this slide. Here also we try to demonstrate the absorption and oil retention of the fiber, because here we can see the absorbency and also retention capacity diagram in this paragraph. And we already tried with different type of oil, three typical types of oil as I mentioned before. In this figure, we want to demonstrate one very important thing of the web is the capacity of reusability. Because normally if you can use as a choice of web one time and throw it away, is maybe waste of fiber and some time. And we try to reuse it 3 times. So here in the figure, we can see that at different time on different circle, we try again how our web can retain on the oil, and this demonstrates that it can reuse for about after 20 cycles use. It's very important because so after absorb the oil, we can squeeze it again by hand or even by some centrifugal force machines, and then we can reuse. And the reuse of the web also one important thing for the saving of material and also the environmental protections. Here is some main conclusion of our work. First, we already improving the oil absorption when compared to the raw K-pop, because when we use only raw K-pop, as I mentioned at the beginning, it's not easy to form the webs. That's why we have to try to mix with also the different type of fiber, and the amount of the oil just can adjust by the K-pop fiber here is quite high, as I mentioned by number in the slides. The second, we already adding in increasing the fiber web forming ability on the laboratory cutting machines, and successfully create a fibrous web with up to about 80% of cable fiber, because we try to upgrade more content of the natural fiber in the mixer. However, when considering the operating environments in river and calm sea, for example, we found that the ideal K-pop propylene fiber ratio is about 70-30. Third, we already contribute to an increase in oil absorption capacity of the form oil absorbent web about 11% over the previous reports. And the fourth, the oil absorbance web can be reused for more than 20 times, and the oil absorption capacity is reduced by only 25% after the first 10 cycle. That means the capacity is still quite high, and the web retains the structure and durability required for the manual reuse. That is four main points that we obtained from the results, and this work was also published in the papers, and we're happy to share with you again today, and hope that we can share some idea, also get some comment and question or information from all of you. So thank you very much for your attention.
Thank you. Thank you for sharing with us this practical application. Yeah. At the moment, I think if there are questions, please feel free to address it via the Q&A chat box.
Yeah.
And if not, then as we see that you will go through a marathon and you will continue also with another research summary with regards to application of textile finishing for bacterial cellulose functionalization.
Yeah.
And yes, so perhaps we can also go ahead then and
Okay.
have a look at this final presentation.
Yeah, okay. I'll just try again the presentation. I'm not sure that can you see my new presentation right now?
No, not at the
it's
moment.
still, okay, yeah, so let me check again. Yeah. So I hope that it is in screen right now.
Yes, yes, now we
Okay.
can.
Yeah, okay, thank you. Okay, so the second result that we'd like to share with you is about the application of the textile finishing for bacterial cellulose functionalizations. Were already done by our group of research group, young research group, and also some, let's say, experienced research group in our department. So today we would like to share about our study about the sustainable textile product derived from the bacteria and nature source, and especially the projects begin with the series of bacteria cellulose study in our department. The contents of our presentation today include the four main points. So first, about introduction, the methods, the results, and so of course the conclusion about our work on the bacteria cellulose. To begin with the section 1, introduction, would like to talk about the environmental impact of textile industry. Honestly, we should draw more attention with serious awareness, because in fashion industry and environmental issues, it has been acid as freshwater depletion caused by cotton farming, pollution, dyeing and finishing distracts, and deforestation for regenerative fiber production. And moreover, in another discipline, humankind has encountered with the global pandemic named COVID-19, as we already know, and that's why there was an immense demand for the disposable face mask. And for instance, the face mask consumption was approximately about 129 pieces per month. Global concerns about the future environmental crisis named disposable face mask has mentioned many times up to now. And turning into the nature polymers named cellulose, we already know that cellulose has a lot of ideal properties such as environmental friendly, as biodegradable, enormous potential for the textile application as fabric productions. Besides, this material is also safe and biocompatible, that's suitable for medical application, and especially cellulose is the most abundant polymer in nature. Therefore, we can find cellulose from superior plant, algae, fungi, and also other special bacteria. In these slides, we mentioned about the bacterial cellulose. because we can consider has innovative and unique property. For example, like the 3D nanofiber network, the hydrophilicity and the high strength, and also the high purity. And in Vietnam, we have advantage for bacterial cellular production such the available of the fermentation system, local resource like especially the coconut farm as a main component to produce traditional bacterial cellulose, and finally the textile facility in our countries. However, there are still a lot of difficulties for textile application of bacterial cellulose material. You can see in the picture, the never dry form contained more than 99 water amounts. That is also a challenge for the current textile technology. And this material was not so popular in the textile industry due to the limited application and also the lack of the productive and efficiency method for current textile industry. In this work, we already apply some methods. We focus on bacterial cellulose produced by Vietnamese advantage like a variable fermentation system, local resource, and to combine with other natural sources like wood, sin, and local herb, and processed by the textile equipment by the padding or exhaustion to produce sustainable textile products. And here's some of our results. We'd like to introduce our achievement that is a fabric-like bacterial cellulose material as a milestone of our study. And in detail, the fabric-like bacterial cellulose material is suitable for the current textile finishing technology. And therefore, this investigation initiates the potential bacterial cellulose in textile industry to produce textiles in medical, technical, and also fashionable application. So there are various related products of our study, as you can see in the picture we post in our presentation. First, for the healthcare, we fabricate various materials for wool dressing application, SBC, collagen composites, and pH sensing part for health monitoring. For the environmental aspect, we initially step forward with the BC filter materials, and for eco-friendly material, the virgin leather is investigated with the same appearance with the true leather, and you can see in the pictures with the red virgin leather we saw in our slide. Therefore, from this introduction about our work, we have some final section. We pursue that the target with our future perspective can be in medical textile. We focus on the wool dressing and biodegradable face mask. In technical textile, we draw more attention for environmental protection material, for example, for textile waste water treatment. In recycle, fashionable, and eco-textile, we have functional sportswear material for thermal control, self-cleaning, and also antibacterial treatment, and also some wearable accessory that we can create from the BC. Finally, I hope that some brief introduction of our group can share with you some thoughts and also some information about what have been done in our laboratory and also our department right now. So thank you very much for your attention, and if you have any question, please send to us, or we can contact via email if we have some common concerns about the results today. Thank you.
Absolutely. Thank you very much for sharing the work that you have been doing and your team has been doing. I'm sure there will be many potential trials and actual projects for implementation of this work and to move it further. As some participants are asking, yes, you will all receive a copy of the presentations. And there is one question for you in the Q&A, and the question is how much it might cost to treat 1 kilogram of fabric with bacterial cellulose. Will you be able to share some feedback?
For the cost, let me discuss with my group a little bit.
Okay.
Yeah, actually, I'm not really remember about the course, but
No problem.
as in, it's not maybe a big problem that we have to concern. As I mentioned in the slide, the material, that kind of material, maybe it's quite expensive in other country, but for us, like with a lot of coconut farm and coconut water, that can be base material for the cellulose. It's not a problem that we could consider about. Let me check. I think it's not a thing that we should consider, at least in our tropical country. So maybe I will share with you. I will give you a detailed answer, because right now I still cannot calculate how much it would pay for 1 kilogram. Yes.
Yeah. No worries. No worries.
Yeah.
Thank you for that. Yes. And then now that we went through this session of upstream innovation, it's also time to get your feedback. So Emma, if we can get some feedback from the participants about what they felt about this session 3, if we can have the poll on the screen.
Yes, sure.
And I think while we wait for our participants to respond to that poll, I would also like to request if the speakers and presenters of session 3 can momentarily turn on your cameras so that we can take a virtual picture. All right. Yes. Thank you very much. I am sure that this picture will be useful when hopefully in the near future, the RUN Symposium takes place in person and face-to-face. And while you are responding to the poll question, we have a final request. You heard about the topic of waste management as participants. You heard the topic of resource efficiency. You heard the topic of innovation upstream. What do you feel we should start up with? Many would say everything is important and we have to start doing a little bit of everything and move ahead. But if somebody were to ask you, what should we start off with first? What would be priority number 1? If you could please click on this link and provide your feedback. The link is in the chat box. If you can please click on the link and share your feedback on what you feel we should be starting with. So we see so far your feedback has been on process improvements, perhaps lots of technologies there, materials are there, and now it's time to implement a lot of those good housekeeping that we heard from Dr. Helmut Christ here.
Should I end the poll or put some more time? I think
let's give a few more seconds for the participants while they also respond to this this question about what do they feel, what do our participants feel with regards to the first priority. So process improvement seems to be the popular one as a starting point to look at it. And while we are looking at it, maybe Emma now is a good time to put up the results. All right, so this is also thanks to you. Thank you for your preparation and for sharing with us. As you see on screen, whatever you have prepared and the work that you have is considered to be satisfactory and very satisfactory with the participants. On behalf of all the participants, I want to say a big thank you to all of you for taking the time, for sharing your work, for sharing your wisdom, for sharing your experience with all of us. Of course, ideal would be that we were all sitting together and that we have some more discussions on this topic face to face. And hopefully sometime in the near future, this will still be possible. It is also a special month for many of you, celebrating the holy month of Ramadan. So thank you for taking time and going beyond the regular working hours to participate and contribute during this session. As you would also know that A lot of work goes in planning all of this. So very shortly, some pictures for you. There are many more colleagues, but here you see on screen everybody who contributed, who participated with the organization. There's of course the consortium led by Adelphi, where there's Reed Consulting, Aspire, TÜV Rheinland who worked on it, but also the colleagues from GIZ themselves in getting all the universities together. The hope is, and the wish is, and the plan is, or the expectation is, that members of the university will find out topics of interest which are relevant for the industry to work on this initiative. GIZ will ensure that they bring in industry. GIZ will also support or facilitate bringing in the technical experts. They will also support and facilitate the dialogue with policymakers in this three-way consortium. Yeah. Before we end, Yugen, Emma or Noor, is there something we missed? Is there something you want to add on?
Maybe we can take a group photo before ending this session.
Yes, absolutely. Yeah.
The question is if Gundolf is with us, who wanted to speak a few final words, but I think he has problems to join.
Yes,
Right,
he's not present.
Yeah. But I think Yugen, you know Gundolf and you know his expectations, so maybe you can share what he would hope or expect or want or desire.
Thank you, Rakesh. I only can join you because your last sentences, what you told last, was a very good final remark. And I only can join you in thanking all the speakers. And I think if I counted well, we had 12 speakers who presented 14 presentations today. And these speakers, panelists, came from 6 countries. And we had it in 3 sessions. And if I counted correctly, I saw the figure 50 to 70 participants, even more. Let me extend my thanks to all the panelists, of course, and their helpers and their co-workers who contributed very much to the research success. We saw the outcome, and it was on a very high level and very, very interesting. I thank all the participants who listened, who were present today, and I would like to thank all the helpers, what Rakesh already mentioned. I would take the opportunity to announce another symposium, which we will have in the same framework and most probably will be organized in June this year. We would appreciate, of course, suggestions of topics and contributions, papers to be shared in the next weeks. I'm sure we have a lot of results which can be shown and we will propose some overall topics so they can be subsumized under different sessions. Again, thank you to all of you. Thanks also, very special thanks to Rakesh, our moderator, who did it again in a very good mode and very interesting. You guided us through the last hours. Over to you, Rakesh. I don't know if you want to say anything.
All right. I would only say that it has been a privilege. It has been a privilege listening to your wisdom, your work, your efforts. Thanks to you, all the panelists. Thanks to the entire Fabric Consortium team. Thanks to everybody from GIZ, and especially thanks to all the participants who took time from your schedule, who asked questions, who interacted. Please take care, and we hope to someday see you, meet you in person.
Yeah, thank you. Thank you very much for organizing a very interesting webinar. Thank you very much, and goodbye. See you later.
Thank you,
so
and
much.
really hope to see you in reality.
Thank you. Goodbye.
Yes.
Thank you. Goodbye.
Bye.
Thank you. Bye-bye.